Awesome. Oh, Nancy Hall's coming on too. Good morning. Good morning, Nancy. Thank you so much
Morning,
for
Flo.
coming.
Yeah.
So
So,
you see, Chris has he asked to record it, so he can record it. I'm recording it. I wonder if you can even record it.
We could actually send them a link to the recording afterward if they're not capable of doing that at the moment. So,
Yeah, and
yeah.
I actually, oh, and Glenn's on too. Oh my goodness.
Flo's excited. Everyone's on.
And Mike was coming on too.
Okay.
you got that.
Yeah,
that
I can
it,
get. Yeah, I can get the link of Flo. I know you put it on the YouTube channel, so I'll
yeah,
grab it there.
yeah, I put it on YouTube.
Okay.
So that's not a problem. Well, good morning, Glenn. I'm so glad to see you. And Nancy and Mike are coming. So this is a school in New York. I think you went to it, Glenn. Did you ever go to Half Hollow Hills with Jean? It was a Jean school.
That was Gene's school.
Did he
Yeah,
did
I don't think I got to go.
Oh, okay. Well, he turned off his background, but his background is a total tech greenhouse back there. It's amazing. When he stops sharing his PowerPoint, you'll get to see it
Yeah.
more, but he turned off some of the lights in it. All right, so we're ready whenever you are.
All right, take it away.
Awesome. Hello, I'm Alexis. I'm Anya.
I'm Ian.
I'm Sophia, and our project is.
Nice to see you all. Good morning.
Good morning.
Oh, I think our clicker might be malfunctioning because we're in share mode. Let me see about that.
Right.
Try now. No. We're going to stop the share just for a second. We always can expect a few technical difficulties, right, guys?
That's
right.
for sure.
So we're just going to try to share again. And I wonder if they give me the entire desktop. That's what I want to do. All right.
Yeah, there's your interesting
Yeah, we've got a lot
screensaver.
of odd stuff. Let's try to get back over to Chrome here. And I think it might be that we're in full screen mode.
And
So
you don't, we see it better when you're in share screen, but
so let's see.
did it work?
It's odd. It's not advancing the
Could it have something to do with the recording?
No, I wonder if it has something to do that I'm projecting you onto my main screen for the kids.
Uh-huh.
I'm going to take you off of that screen and just keep you on the little guy, and we'll see if that doesn't change things.
Sure. You see that greenhouse behind them?
Yeah, that looks amazing. Looks like you
It
guys are
is
growing all kinds
amazing.
of stuff.
It is. Yeah, he does.
All right. Now you guys try. Yeah, okay.
Yeah,
We're
it
better.
worked. Yeah, it worked.
All right. Cool. All righty.
Okay. Half Hollow Hills High School, east. So that means there's something west, or
Yes, we also have a web.
okay.
All right, good morning. I'm Alexis. I'm Anya.
I'm Ian.
I'm Sophia, and our project is a rejected robot. The problem we're seeking to solve is a lack of data about the lunar surface. Specifically, we aim to capture images of the lunar surface via a small, lightweight robot, a goal that has not been achieved yet. So our criteria for our project is firstly, we have to design an ejection box that will eject our robot to survive a 6-foot drop. And our robot must land between 24 inches to 36 inches away from the lander. Once our robot lands on a new surface, it has to operate autonomously for an hour and has to take photos via camera that uploads the photos to the spacecraft.
We have some constraints that we have to follow. Our first constraint is the limited space. The ejection box must fit within 6 inches by 4 inches with a height of 5 inches. So the entire ejection system and the robot has to fit in within that space. Another constraint we have is weight. The robot has to weigh less than 15 ounces, but still has to be durable and survive the 6-foot drop. There's still the constraint of temperature. The The moon has harsh lunar conditions, with very hot temperatures and cold temperatures, which the robot has to survive. And the robot should be sandproof. The entire lunar surface is covered with sand and dust. And so the sand should not get into any wheels or moving parts of the robot.
So when we began researching our robot and looking at ideas, we began with the scan robot. First thing that we found that we liked was the Blue robot, and we liked this because it fit within our constraints and our criteria, as it fit within the palm of our hand. We also liked that it had a long battery life and the fact that it used a Pi. And we liked a Pi because it's not only convenient, but it's also easy to cook. However, upon more research on this Blue robot, we realized that when operating on the moon's surface, the wheels it had with them, the lunar dust would get stuck in the joints. So that turned us to look at rotor wheels. However, when it came to manufacturing rotor wheels on a smaller scale, we realized that wouldn't necessarily be feasible. So that turned us to the Sphero SBRK. And because it's in an enclosed sphere, we wouldn't have sand getting the joints, allowing it to align with what our project's ideas are.
So when researching ideas for the camera, I looked at the existing camera that they used during the Apollo missions, and that was a Hasselblad 500L. And from this, I gathered that they don't use any special filters on the cameras. There's no infrared filter, but they did use a flash. So in our robot, we're going to integrate what we learned from the Hasselblad by using a Pi cam with no infrared filters and flash. And on top of that, we're going to have a panel movement so that we're able to, the point of view of the camera is not restricted just one point of view, and we're able to look at the ground and the sky, and we're going to achieve that using microphones.
So when we looked at alternative solutions for a robot, we start off with our wheel, which we once again liked for its small size, the fact that it uses micromotors for wheels, the convenient use of the Raspberry Pi, and also its long battery. We found that it also has GPIO pins. However, what we did not like was the fact that it did not have a CSI port. So that means we couldn't necessarily add a Pi cam, which wasn't necessarily aligning with what we needed for our project.
So our other solution was a Sphero robot, like Anya mentioned, it's a ball robot. So this way there's no dust that's going to get into the robot and prevent its function. There's also a gyroscope, which helps maintain the balance of the robot. So if we were to add a camera, the camera would always be upright and never be tilted upside down. There's also Bluetooth control up to 100 feet and a battery life of 1 hour, which is the criteria of our robot. However, there's no GPIO or CSI port, so we're not able to attach any additional modules like or the Pi. So our proposed solution is to scan for the drive components and the general layout of the Sphero robot. We accomplish this by using micromotors for the drive system. Those micromotors are going to have a gear attached to its shaft, and that gear is going to turn a second gear that's located behind a set of wheels. That's going to generate movement. On top of that, there's going to be a second set of wheels at the top part of the robot, and that's just going to help make movement more smooth and just help guide it overall. The main brain of the robot is going to be a Raspberry Pi Zero, and that's small enough to fit inside a robot, but still contains the GPIO pins and the CSI port. And from the Raspberry Pi, we're going to connect a Pi cam, a micromotor, and various micromotors for the camera movement. And we plan on using a weight at the bottom of the robot so that it stays upright. And also, additionally, we're going to okay, so future research of the robot right now, our main focus is working on a drive system so that we have a robot that can operate autonomously on the moon as a ball. So we haven't worked on a plan for creating a flash for the camera or a gyroscope. We're looking at gyroscopes and magnet heads to make sure that the camera stays upright.
So next, we had to look at how we are actually going to eject the robot in between that 2 to 3 foot distance. So we looked at 3 different ejection mechanisms. Firstly, the scissor unit, as depicted on the right, essentially working as almost an arm, retracting and deploying. Next, we looked at springs. There's over 10 different types of springs. We found that compression or conical would be best utilized for our main goal. Lastly, we have air pressure, similar to a nerf gun mechanism. When looking at alternative solutions, we wanted to look at potential energy as well as efficiency and power line review. Firstly, with our spring mechanism, we found that the outcomes would be less consistent, but the potential energy and kinetic energy could be calculated how much there would be. Next, the thing with the springs was it was more simple. There were less moving parts. Lastly, there's just a maximization of potential energy overall when compressing a spring into a quarter of itself.
Another alternate solution that we considered was the scissor unit. As you saw in the slide previously in this slide, there are two states of the scissor unit. In its retracted state, all of the joints are vertical here, which makes it nice and compact. And then in its deployed state or extended state, all of the joints go horizontal, which extends the arm a set of distance. This is good because it guarantees an extension length, unlike our other solutions, which has some other variables that can affect them. It's also good because it's very compact, which helps fit our criteria of our limited space. Some problems with it is that it is more complex. There are a lot of moving parts with it because there's a lot of joints there, and it does require multiple motors, since we do need a motor to extend the arm, and our solution for grabbing the robot would be an arm at the end of it, which would also require a motor to keep in place and then release.
Lastly, we have the air pressure mechanism. The air pressure mechanism would require multiple pressure points, and it would be more complex. Also, it would be bigger. Furthermore, it would require multiple motors to function, and we do still have a limited space of 15 ounces. Lastly, it'd be harder to test on Earth compared to the lunar microgravity.
So for those reasons, we decided to go with the spring mechanism because it is more simple. So, well, for the spring mechanism, we do need to decide what kind of springs we use. Throughout our research, we found two springs that really caught our eyes, which were compression and conical springs. Compression springs are common everyday springs, which are much bigger than conical springs. They compress down to a bigger amount than conical springs, but because of this, they do release more energy, but they also do need more space, which is a problem with our compact designs. But conical springs, they're made to compress down to a small amount, which it does help our constraints of a small space. Except the problem is because of its design, it does release less energy, which requires multiple conical springs to release the exact same amount of energy that one compression spring would. So we decided to use less compression springs, which would help our design. So we decided to go with compression springs.
So depicted to the right, we have an orthographic sketch of our potential ejection box. As you can see, we have our spring mechanism with the compression spring, and we want to utilize horizontal spring action to eject the robot. This parallels everyday spring action of heads and nerves. We were planning on having a spring contact point on the actual bot, in which there would be springs in a circular format of 4 to 6. The spherical robot's design and the borders on each side allow for a lack of alteration of the actual ejection mechanism during the flight to the moon.
So here we have a 3D CAD model of the ejection box. As you can see, there would be our main solution here with that there would be a barrier in front of the robot. The idea is that the robot would be loaded on Earth. Whoever's loading it would push the robot all the way back, which would compress the springs and make it flush to the wall, and the robot would be kept in this position with the barriers on each side. And then the barrier in front of it would be lowered down, which would also be flush with the robot. This prevents the springs from releasing their energy too early, and not until the barrier is moved up. But some future features we do have to consider is how is the barrier going to move on the moon. We could add a motor, which would move the barrier up, or we can make it manually activated. Another thing we have to consider is that the robot does have to be charged upon ejection. An idea we had this is that Sphero has wireless loading charging docks, as you can see in the image on the bottom right. So an idea we had was putting that at the bottom of the ejection box, which would keep the robot charged until ejected. But then if with the charging dock, and if we're going to implement a motor to move the barrier, this would need a battery in the ejection box, which we could add in front of it, but we do still have to consider the space. Thank you. Do you have any other questions?
Great job, team. So right now you're looking at using a Sphero, and that's great. Is there going to be a problem with the surface of the sphere getting scratched up or anything for the as it hits the ground for the view of the camera?
Yeah, that's definitely something you have to consider.
Okay.
I can't hear you very well. Could you move over closer to the microphone? I think it's just your positioning there.
It's a concern that we were worried about, but as of right now, we have to look into the materialization of any. But we will look into.
Okay.
Okay.
And I think that the Sphero uses like I think it's an acrylic ball. Is that correct?
So it's like somewhat of a like acrylic plastic. But we're definitely gonna look more into the material that we actually.
Yeah,
And acrylic's actually a good start because it's better than some others. But so that's good. Go ahead, Nancy. I'm sorry.
yeah, no, I was gonna say, yeah, you're correct. You could, for your final, for what you want to tell us is for the final version NASA creates, this is the material you want us to use, um, and so forth. So, and I have another question. Glenn, do you have more you want to bring up?
Go ahead, Nancy.
Okay. In one of your pictures that you were showing the wheels, and I just want to confirm, is the wheels inside or is it a little bit outside? Because I'd seen one of the pictures and it looked like there was a couple of attachments and then there was a wheel. So just wanted to confirm and make sure I understand where if there's still a wheel, or is it moving, or is the wheel inside and that's what's moving the sphere, or is it outside?
The wheels are inside. They're on the
Okay. Okay, I think okay. So then the picture, I think you were just showing what it looked like, and I wanted to confirm it was inside. Oh yeah, with you guys there, I can clearly see the plans. So I think those look real nice, and the purple light over there. Cool.
Yeah, the plants are awesome.
Glenn, you muted. There you go.
The so Sphero is weighted at the bottom. Why do you think you need a gyroscope?
Well, we were looking at the gyroscope because we were worried about the balance aspect. Also, because if we use a weight on the bottom, since we have a maximum weight of 15 ounces, that might be a little bit tricky. So we kind of have to balance our two options here and kind of weigh them against each other. So that would be part of our future research. But right now, we're trying to figure out the technicalities of it. It's actually implementing the gyroscope is something.
Okay. I suspect that your weight, you should choose one or the other. If you have both of them, I think you could have some conflicting forces in there. Okay. Excellent job. Flo, any questions for you?
No, I like that. The only thing I'm worried about is the camera. And I'm always worried about the camera. That's an important part of your project, right? That it has to turn around and take a picture. When it lands, it's going to kick up dust, right? So somehow, if you could maybe even have like a blind, a Venetian blind or something on the outside of the cameras, so that all right, it got dusty when it landed because it could land right on the camera, right? Then it would be protected somehow, and then it would open the blind and take a picture. I don't know, but I'm always worried about that camera because we want it to work. Does that?
Because if you were to eject it, the weight would make it that would then.
But the camera could still get full of dust because when it hits the ground, it's going to kick up some dust. If you watch videos of the Apollo mission, the astronauts, the feet of their astronauts' spacesuits are pretty dirty from just walking on there and kicking up the dust. What do you think, Nancy and Glenn? Is that an issue?
I'm sure that there will be some kicked up. I think most of the dust is going to be kicked up just from the engine as it's landing. And it's going to be fairly close to that. So unfortunately, no matter what we do, there's going to be dust in the way. So I think their plan is very good. And I think that they should continue with that.
Yeah, and I was going to add, that's why with a lot of the rovers and everything else, NASA, plans for like a day. In this case, we're planning for what is it? A short amount of time. Because you're right, eventually it'll get in there both on the moon and Mars. But for what you're planning to do in the time frame, that's why we want you to test it. Beforehand. From the testing, even though it's only, I think, what is it, Glenn, 30 seconds or so many feet they need to move, you can do enough testing to see how much of an impact that would have on your design. And that's the key thing we're looking. We're looking to see it does move, it's able to meet these requirements. And if it doesn't, that's where you want to do some additional research. And that tells you about your design. It may not be strong enough or fast enough, or there may be other things in there.
So
Awesome.
I was just thinking, because it's a ball and there's wind coming from the lander's engine, is there a chance that it could be pushed back by the wind?
Is it being ejected while the lander is coming down?
That's right.
It depends on where it is. If the lander is coming
No, it's
down,
only 2 to 3 feet away, so it's
yeah,
got a lot of breeze. And
Yeah.
so
yeah, it
I
could
don't have an
conceivably,
answer for that,
yeah.
and I don't know how much power this engine is going to have. And
Mhm.
so this is just a question for you guys to contemplate. Okay, it's not a criticism because I think that you guys have a really solid idea here, but it is something that you'll have to consider. Okay,
All right. Thank you, guys.
good job, team.
Yeah, wonderful
Nice.
Do you have any
presentation.
questions for us?
So what I actually have, you'll note my little AI note taker is also on the meeting with us to take your comments for the kids because sometimes it's hard to digest in the middle of a presentation. So if we do generate some questions for you all, perhaps we could forward those to Flo after
Yeah.
our meetings conclude today.
You bet.
That's
You
terrific.
can always do that.
All right. Awesome.
Thank you. Nice presentation.
Excellent
Thank
job.
you, everybody. All right, so I've got my next team in queue here. We've got a lunar camper design team that is joining us.
Okay.
And
Yeah, Flo, I got a 9:30, so I'm gonna jump out in a little bit.
Okay.
I'll listen
But
to as much as I can.
yeah,
When,
thank you so much.
while I'm getting set up here, I heard a rumor that you're going to be in San Juan with us in December. Are you going to ASGSR also?
Oh, yes,
Nancy is.
I am.
Yeah.
You're gonna be in San Juan too?
Yeah, we've got a team presenting at the poster session on behalf of Growing Beyond Earth. So they were
Oh,
invited
awesome.
here, actually
Okay.
attending on a scholarship. So that'll be
Oh,
neat.
perfect. Yeah, because I also have a student design challenge I do for drop towers, and I'm going to have students. In fact, I'm giving a presentation on HUNCH at one of the education sessions too.
Oh, awesome.
So actually, Flo, it's our presentation we gave at SEEK. I'm going to
Yeah.
take
Yeah.
at ASGSR. So, and you're Chris Regini. I will look for you, Chris.
Yeah.
Awesome.
Definitely.
All right.
Should.
So I've got my next team. I'm going to go ahead and share my screen again.
Okay.
Have a great weekend, everybody.
Enjoy the weekend.
Yes. It's a long weekend for us. Well, at least for us, Monday is a holiday. I don't know if you guys have school.
We do also have the holiday on Monday.
I like that. Glenn, did you see that Flintstone?
Flintstone.
Have they been watching the Flintstone? They're too young.
Yeah, they're way too young for that. Somebody told them about it.
Somebody
Though.
told them about it. Oh,
I
that is
actually just told them about the theme song today, that it should be spooling in the background, and they shot me down pretty quickly. So
I actually used to love the Flintstone.
oh my God, I did too.
all right. Are you able to see their screen, guys? Can you just confirm that we can click through the slides? We had a little technical difficulty. Cool.
Yeah, we see the screen.
All right. So I'm going to introduce you to my next team, and I'll let them take the stage.
All right.
Hi, our project is the Flintstone Lunar Camper Model Z. My name is David Sanwa. I'm John Astarakis.
I'm Carly Lansky, and two of our teammates could not be here today, Cole and Amanda. Our teacher is Chris Regini, and we are from Capitol Hills High School.
So the problem. The astronauts, when they're on the moon at the lunar base, they're going to need a lunar terrain vehicle in order to expand beyond the base to complete their research. But in order for them to complete long-term research, they're going to need a lunar camper that will allow sustained living. Our focus of the camper is on the collapsibility, exterior design, mental health, and utilities of the camper.
The criteria and constraints are constructing a lunar camper that can fit within the specified shipping volume and be assembled on the moon without taking a significant effort. It also has to be able to sustain 2 crew members for at least 2 weeks away from base.
one of our teammates, Amanda, was very interested in biomedical side of the competition. So she designed a mental health space for the astronauts. She decided that incorporating a green space was very important. So she had the idea of a green wall. She also thought that colors were very important for the astronauts' well-being as they promote different moods. She also decided to incorporate an IV fluid station for the astronauts for their overall well-being. And many, she also had many ideas like a family photo screen and incorporating an AI therapist for the astronauts' mental health. This is a chart of the different colors that she researched that promote different moods for the astronauts. As well, she also decided that putting LED lights around the camper would be a good idea to implement this solution. This is an example of a green wall that she found that will be used in our design.
So I was really focused on the exterior design of the lunar camper because personally I'm very interested in vehicle and car design. So when I was looking at all the projects, when I saw that there was a lunar camper that had a little bit of that interest incorporated, I knew that that's what I wanted to do. So originally I was looking at different SUVs and also just campers on Earth. But then I realized that there aren't as many atmospheric restrictions on Earth as there are on the moon. So then there's a lot more flexibility in terms of the design. So then I was really focused on using organic design elements that aren't commonly found on Earth, on the moon for our lunar camper. So even on the right, you can see I was looking at these are Yeezy Foam Runners, which is a kind of shoe. So I was really just looking at that for a little bit of design inspiration. And this is kind of just a few more of the ideas that I was looking at, specifically just with the gradients and the flows of the exterior design of the camper. So I was also looking at the rear end and the rear end of the wheels and just the wheels as a whole. And I found that having larger rear end wheels for the camper would actually allow for better traction and straight line acceleration, which is super essential on the moon, considering there aren't like roads and, as flat terrain as exists on Earth. I also looked at having the wheels not directly being inside of the wheelbase because I found that it would add a little bit more interior space for the camper, which is essential due to the collapsibility constraints. And it would also allow for greater suspension, which would mitigate the rocky terrains that exist on. So these are just some of the original sketches that I came up with. On the right, you can see I was playing a little bit with the rear end larger wheels. But then as I was developing the idea further, I was also thinking about the different elements that exist on vehicles on Earth. And I was thinking that a lot of them could be directly embedded into the shell of the lunar camper, as you can see on the left with the embedded lights, just to allow for as much collapsibility and as much compactability as possible. So this is really the final design that I came up with in terms of the exterior design of the camper, which implements the larger rear end wheels that are not directly inside the wheelbase. And I was also looking a little bit with the collapsibility of the camper. So I thought that there could be metallic wiring that could fold outwards, and then there's inflatable and expandable material in between that could then expand outwards for the camper, just allowing for as much interior space as possible.
I was focused on the floor plan and collapsibility. I'm very interested in architecture and the floor plan of the camper. So this was some of my concept generation. This is just all the things that we need in the camper: the foldable walls, the space for electrical and plumbing, space for astronauts to sleep, eat, do their daily tasks. This is pictures of NASA's temper foam that I was thinking of using for the beds, and I was also thinking of using Murphy beds.
If you signed up for the Wilson Tech Radio
Some of my
Station,
research included
Thursday,
Murphy
November
beds.
Can you just pause for a second, guys?
Get a
Well,
pass
the
from
squawk
the-
box. Sorry
Yeah,
about
yeah.
that.
Thank you.
All right, good.
Some of my research was the Murphy beds, collapsible tables,
And on the right is what I was thinking about doing for the water tanks. This is some of the research I did for the floor plan, just looking at what tiny homes had for their floor plans and thinking of what I could do to implement it in the lunar camper. This is some of my designs for the roof. At the bottom, it shows like a fan, like expandability. This is the floor plan that I decided would be useful for the lunar camper. On the right is the overall floor plan. On the left is the design space for the green wall mental health space. So on the right, there is a space for the astronauts, the airlock for the astronauts to get in, a bathroom, a lab, expandable water storage, a table for eating, and it is about 9.5 feet tall. So I was thinking about doing Murphy beds overhead and that fold up, and underneath would be the mental health space. This is us designing the floor plan and actually stepping into it on the floor in the hallway. And we made a few adjustments because we were able to actually see the space. We made a prototype made out of cardboard, and this just shows our original ideas for how it would expand with the fan out roof. And later we combined both my ideas and David's ideas to create a new prototype that we're in the process of working on now.
So I was in charge of the electrical and the plumbing. So for when I was developing designs, I realized that there needs to be an immediate and possibly a backup source of power alongside maybe storage of power. And for plumbing, it needed to be able to fold inside the hole and also be able to go across the hole while also providing proper water flow in the low gravity. For the plumbing, I looked at bendy straws. They can very easily turn and extend, and they're pretty compact if they're fully enclosed, and fully expanded, they can stretch a decent distance and make sharp turns and fold, and it just looked overall a good idea. As for power, I kind of had a multi-stage system. For the first source of power is the solar panels, which would line the hull of the exterior, which could be good as long as there's a line of sight with the sun. There's also regenerative braking applied from electric vehicles that could be used to generate power in as long as it has motion, it could be used to stop it as well. There's also an RTG in case there's no line of sight with the sun and maybe power is low. It could work as an emergency solution in case they overextend their expected power supply. And of course, there's a power storage system, probably consisting of a battery or two. I was also in charge of installation. For both designs, for the first idea for installation, I looked at spaced armor of tanks, and I tried to create like a pressurized, depressurized, alternating zone of really thin sheets that would prevent heat conduction with the outside. And for the second idea, I looked at aircraft, which use polyaramid monofilament foams that could also provide good heat conduction, but they could also be heavier than the alternating spaces. Materials was made by Cole, but he's not here today, so I'll be presenting on his behalf. Research, we looked at Smart Tire Company and Integram. They made the Nitinol and Nanovate alloys that we were planning on using. For generating ideas, he looked at a lot of materials like fused silica glass, which can withstand high temperatures and also block out certain levels of radiation. He also looked at aluminum alloy 2219, which could be used for maybe a skeleton structure or for important structural elements. Looked at a few other elements as well. For the wheels, he looked at nitinol wire, which NASA is already experimenting with. It can withstand both extreme heat and extreme cold temperatures, and it can deform up to, I'm pretty sure, around 80% and return to its original state. He also modeled the project, which implemented designs from the entire team and kind of just turned it into a 3D design that we could kind of get an idea with and see. He split it into the exterior, interior, and the wheels and the drivetrain. The exterior has just the exterior shell and an exterior wall. The interior tries to use as much space as possible, minimizing any actual thickness of the wall. The wheels and drive, the wheels are made of nitinol, as I said before, and it has a simple frame to kind of save on parts and save on space. And that's the total design complex of it.
So this is the aspect that we're really working on now, it alludes to what Carly was saying earlier on how we're combining both of our ideas. So we actually came up with this concept. We're calling them Z-beams, which is essentially a way that the entire camper could fold and expand outwards, which would allow for a lot of interior space while also being very aesthetically pleasing to the eye. Thank you.
Oh, wow.
You guys got a lot going on in there. So do you guys have your cardboard thing that you can show me how it opens out?
So the young lady that was going to demonstrate that, we ran a little bit over. She had an AP test this period. I'll go see if I can dig it out of the back for her, though.
It's okay. And so part of my question is just that you get 1.5 by 1.5 by 2 meters, and getting all of those different ideas into that looks complicated. Have you started with, here's my starting dimension, and then seeing how much you can expand out to?
Yes, that's actually what we're working on now with the Z-beams, and specifically how we can expand it as much as possible in all 3 dimensions, allowing for all the interior components that we were mentioning earlier inside the camper.
Okay. And could you pull up your slides again? I wanted to look at your CAD drawing of the you've got the 4-wheel vehicle.
Yeah, let me.
There you go. And then one up.
I don't think this is actually
there.
Okay.
Yeah. So can they stand up in that?
Not at the moment, but this is essentially the rudimentary drivetrain. So there would still be more added to it. It's essentially just the most basic components of.
Okay, so is it driving or is it getting pulled?
It would be pulled.
Oh, okay. And so some of those wheels are going to have to be able to turn then, right? Okay. Just be aware of that, because that is a complication there. It adds weight and it adds some complexity to some of your wheels. So can you go back to your CAD drawing of what it looks like? Okay. And so being able to stand up, to be able to get into their spacesuits is going to be important. So, if you're going to be out there for 7 days, you want to make sure that you've got the headroom to be able to put on and off some clean clothes and things like that as well. So is that a hatch that's pointing towards us there?
Yes, that is. I think that's the most basic components of the airlock that we're currently looking at for the camper.
Okay, And so try not to do an airlock. That's a lot of volume that you're trying to not use up. The suit ports is what I was trying to look for. Does that make sense?
Yeah.
Okay. What's on the other side of that? What other kind of components are you guys putting in there?
On the other side of the camper.
Yeah, if you just turn it around to the opposite side, do you have other things visible?
On the other side, I believe that's where Cole wanted to place the suit port actually for the camper itself. So then the window would be on the front like a regular vehicle, and then
Okay.
on the side that we can see would be the airlock, and the other side would be the suit port.
Okay. Right. And the airlock's just for like a baseball size rock that needs to come in, right? Okay. Very good. And you mentioned solar panels. Where did you think you were going to put your solar panels?
I was thinking of making them kind of like wrap the hull almost. Like not really be like a external extended outside of it, but kind of just attached almost like lining the hull as a shell.
Okay. And there's some good smarts to that, just because they're going to be on the South Pole, so the sun is never going to go overhead. It's always going to be on the horizon. Does that make sense?
Yeah.
Yeah.
Okay. Good job. Keep going. Flo, did you have any thoughts?
Yeah, I absolutely love the creativity. First of all, thinking of mental health. That is so important. And of course, I love the green wall, right? But the green wall actually can serve a lot more purposes than mental health because they can also be growing some of their food in that green wall, right? And it changes carbon dioxide to oxygen. So there's a lot of benefits to that green wall that you were projecting in your mental health thing. So I really thought that was an important part of the project that, of course, no one's thinking of that, right? But you're surrounded by green, healthy plants. So that comes to mind, which is really good. I loved, David, that you thought of a creative design. I loved your drawings. They were super cool. And believe it or not, coolness matters, right? You want to jump into this camper and enjoy yourself. Like on Earth, when you get, hey, it's a big vacation when you get to go into a camper. So and it was really super cool. So I really like that you were doing that. And I also appreciated Carly, who was thinking of NASA foam. No one has mentioned NASA foam, but I guess I don't know the history behind NASA foam, but I guess they used it for space. Do you know, Glenn, the history behind NASA foam?
It was used on the seats for the space shuttle.
For the seats. So it's probably pretty light, would you say, and compactable?
It's mostly made to be soft and squishy.
Soft and squishy.
All right, I'm gonna actually I have to transition this team out of their presentation. I've got two teams lined up behind them. I'm just trying to keep them on track with getting in and out of their classes. But thank you very much, camper. And I've got a second lunar camper team coming up to talk to you now.
Awesome job, guys.
We'll talk to you soon,
Thank you. Have a good weekend. I could go on forever with the things I liked about it. Yeah. Please keep us on schedule.
No, not at all. I always hate stepping on enthusiastic conversations, but I know that
Yeah. No.
luck conscious sometimes too with the kids and yourselves. See you guys. What's up? No. If you guys have to go to another class, then Chase and guys can present on your behalf. But no, we are running like one group behind at the moment. All right, so
to save a little bit of time, they don't need to tell us what the constraints and requirements are.
Yeah, that's what I was trying to tell them when we were practicing.
Yeah.
So skip over, the problem and the criteria and constraints. They know it because they put these all together for you, so you can kind of glaze over that and get to the meat and potatoes of your solutions, okay?
Okay.
Yeah, that's what we
If
really
you got
want
a
to.
prototype, you can show us prototype first. How's that?
Okay. Yeah, so just one of the little basic pieces you've created there in terms of collapsibility.
Oh,
So-
Yeah, show me that.
Oh, hi, my name is Brian Espinosa.
Hey, Brian.
My name is Jay and Che, and we are lunar camper team, half of it, because two of our members are out today. So
Okay.
this is one of our proposed designs, and it's basically like an accordion where you can stretch it out, and you can collapse it back in. And there would be another one of these on this side, so it would collapse to maximum space. The one problem that we had with this design prototype was that it would be impossible to keep this airtight while expanding because it would be a vacuum and it could not expand. And
Okay. So I like your accordion idea there. That's actually really cool. And so you're saying, so right now your dimensions that you're showing me is you've got 1.5 by 1.5 on the bottom, and then it's 2 meters going up.
I think it's 1.5 meters wide, 2 meters long, and 1.5 meters tall.
Okay. And so how are you going to expand it so that people can stand up inside?
It's going to be sideways, so this would be the floor.
Okay. So does that mean that they have to crouch down most of that time, or when they're inside?
This isn't our actual design that we plan on going with, but it was a great idea before we realized that the vacuum thing.
Well, and part of what I'm suggesting is that if you make it 2 meters tall, then you don't have to expand up, but you can still expand out in the other directions. Does that make sense?
All right.
Skip.
Okay.
Okay. So we researched how we could make this thing expand first, because that was our biggest thing. The bus stuff that you see on the left is more about this design, making sure that air didn't escape while we had this, because obviously if 4 walls at the end, there's space in between, and something that was built to take the shape of the actual, the camper itself would help us to get more solid ground.
Well, and that looks good. I'm agreeing with what you're suggesting there. That looks like a great idea. You can expand out in either direction using that kind of accordion style.
Yeah, that's what we called it. And
okay.
So the other design is more it's more more compact, and it's less about expanding like visibly, more like
origami. It's just folding out like piece of origami.
And that's fine. So what are you going to put inside? How are you going to so we've got some expansion. How are you going to outfit the inside of it?
Why don't you go on to the slides where you show the
interior? Okay.
Okay, skip to the interior.
So what?
No, okay. So this was our floor plan for our final model, which we have a prototype for that we can show, not here, but on the slides, which folds folds out from the leftmost photo to the right, and it allows for us to, expand it from the size limitations to give much more room. But we would also need to take into account what we're going to put into it needs to collapse completely so that it's able to fit while it's being transported.
And so over here, we see that most of the stuff will actually collapse onto the wall. For example, the beds, they will be attached to the walls. If you've seen the ISS, they're basically sleeping bags that are attached to the walls, and you basically mount yourself onto the walls, and then you sleep there. Same thing for the table. It's basically just gonna fold up so that they would be able to fold back. And for the soup ports, they will be integrated into the walls. Most likely, this will be the wall that we on top, so that there will be room for the soup ports to be integrated into the walls.
So
okay,
a little bit.
Can you go back to that picture? Okay, so I like your idea. I see how the soup port 1 is over some clear space, but your soup port 2 means that I'm going to be stepping out onto the tire. Is that accurate?
Yeah. That's.
And is that are they on the walls that expand, or are they on the walls that are rigid?
They're gonna be on the walls that expand, but although they're gonna be integrated onto the walls, they're gonna be on the topmost layer, so that it will allow for some integration in space.
Okay.
And basically, this is going to save stuff.
Okay. Let's move over to energy. We plan on integrating a solar panel onto one of the walls of the structure so that we can give power to batteries that would be inside the walls or the floor. Yeah. And we're also aware that we would need light around the camper itself. So we plan on implementing that being powered by the solar panel.
Same for the foldable designs. Pros of it, very compact. It could be airtight. We have a solid base, but thing is, although we're choosing this design, it will be very hard for the astronauts to manually open it. One of our solutions would be use like a string to pull it down. Although it seems hard, putting electrical hinges would be a big hassle because it only needs to be unfolded once, and once it's unfolded, it does not have to be put back.
Our
Very good.
Is the one we mentioned before, which is capable of having lots of space inside. It's much simpler to get to its full size, and it has fewer contradictions.
Okay. So now how are your wheels going to fit inside? Because those are, so you collapse it. Do they fold under? Are they contained within to be able to fit into the box?
For this idea, we planned on having the wheels more on the wall of the
Okay.
each side of
but of course they also still take up space. So you might have to have some indents or something like that for them to fit inside.
Yeah, we were probably into the wall itself, but since we're not using the idea, we didn't go that deep into the thought process. But
okay,
all right, I'm gonna
very good.
I'm gonna collapse down the time just a little bit for you all on the presentation because I know that your team really your emphasis was on foldability and collapsibility, and I know a lot of the other design elements at the moment you're not going to be able to speak to. I think Glenn gave you guys some good things to think about on that level for your team to continue evolving your project a little bit.
Right.
Mentors, any other things you want to say before we have these guys push on to next period?
Yeah, that was very nice. I like the accordion style. One thing you always have to keep in mind is the air. We don't want any leaks. So it's going to be completely enclosed. So design it so there's no connections that make any leaks. Otherwise, I like what you're doing so far. Good job, and I like that you could take over when two people were missing.
A quick
Excellent job, team. Good job.
Sure. Go for your question.
If it isn't completely able to, if it doesn't keep the air in at first, can it expand and then have, the air?
Interesting question. So
I'm not sure, right? Because at what point is it sealed so that then we can fill it up with air?
Yeah.
It's better if you can start from having it, like a basketball. Can you expand the basketball if there's a hole in it, right? So you probably want to start with a position where it's already sealed, and then you expand out to where to the distance, and that whole time it should probably be sealed so that you don't have to figure out how to close up any gaps.
Right. That was a good question. And Dave Schlichting is here too. Dave, did you have any comment?
Well, I want to clarify something with Glenn, but I don't want to take up these students' time on this, so I'll wait on that. I get the sense that what you're asking is how much pressure can you apply to get this flexible material into the shape that you want it? Is that right? It's almost the question of do you inflate this like a bouncy house where you just put a lot of air inside, and once you reach a certain pressure, it allows this thing to push out and take the shape? If that's the case, you may be able to put a bladder within that flexible material itself. Mm-hmm. Do you understand? Right? Your flexible material is going to be multiple layers of different stuff, right? Some of them are going to be there to confer, a little bit more protection against micrometeorites or something of that nature, and others are just there to, prevent the, internal air from leaking. But you can, within those layers, put a bladder that could be inflated with something like nitrogen gas. It wouldn't really take a lot, but it would then help to give you some shape.
Okay, we need to let them get going, and we got to get the next team in here.
Nice job, guys. Have a good weekend.
Have a good
Thank you.
All right. So I believe we're transitioning into a landing leg. No, I'm sorry. Our final ejecting robot before you then bring on, I think Tri-County comes in behind us.
Yep.
So
Tri-County does.
I know that we're running about 15 minutes behind, and I apologize for the delay.
That's okay.
I think it's a large portion is our fault. So
yeah.
No, that's okay. So like Glenn, I said, conversations are good.
Yeah.
You guys got a team there lined up, ready?
Yeah, they're ready to go.
Good.
Yeah. Tri-County, do you have time to wait for us? Awesome. Thank you. Yeah, Tri-County goes to class all day.
Oh, okay.
Yeah, so that's the clear. So guys, again, we're not going to define the problem. We're not going to go over criteria and constraints. We're going to just really hone in on your solution and the evolution of that, okay?
And introduce yourselves.
I'm Chase Lincoln. I'm Yama Plaja. So, I mean, like you guys said, we don't really need to go over the problems.
Yep, go past it.
All those.
So this
okay.
We were
go short on this, but tell us what you're thinking.
Excuse me?
Go short on this, but tell us a little bit about what led you here, okay?
I'm gonna start off with a drill design you can see in the top right. And we would try to make it kind of like what you're seeing now. But we realized sometimes it would be hard to actually have friction and move on the surface of the moon. So we decided to go more with a wheel format, which you can see in it's like top, middle, and bottom right.
So for our earlier two prototypes, the screw propelled design would utilize Archimedes screws, which would propel itself forward. However, we felt that it wouldn't stand against the lunar regolith. It would struggle to locomote. So we scrapped the design. For the two-wheel design, we came up with an umbrella design. However, it was overly complex. So we removed that feature, but we kept the rest of the design.
So adding on to them we developed this main design with so by looking at it from a top-down view, you can see the cylindrical chassis and the tail part of it, as well as the two wheels that we have. So like you said earlier, it utilizes the two wheels along with the tail that sort of acts like a chassis as well as a stabilizer. So going further into the tail design, it's going to be a deployed tail, which means that at first it'll stay within the main chassis of the robot, but then after getting onto the lunar surface, it'll deploy the tail. And doing this allows us to help stay within the size constraints. So it's pretty helpful. Additionally, with our two-wheel design, we're going to use differential steering, which is pretty much tank driving. So if the two wheels want to move in the same direction, the motors will. But if they want to turn, the motors will have to work in opposite directions. And this is helpful. The tail also is helpful here because it helps stabilize it, which makes this possible.
So for the two-wheel design, we came up with two ideas. We had a design which had a fixed tail and wouldn't deploy. And then we also had a tail that would deployed. So you go. So for ejection, we utilized the same method as for CubeSat ejectors, where we'd have a compressed spring, which ejects the robot out. Yeah. And for the
Want me to do it? Want me to do this slide?
Yeah, you did.
So we have our two methods of landing. Originally, we had a fixed tail idea and a non-fixed tail idea. For our fixed tail idea, we can do both methods of landing. A landing with a string and a landing without a string. So with our unfixed tail, we can use the string method. We can only use the string method, which is we're gonna drive our robot out very fast, and then we're gonna use our momentum to get the front of the robot facing forward, and the string is gonna be keeping it in place, and we're gonna get it to land the way we want it to land. And with our unfixed tail, the string is gonna pull onto the tail, and we're probably gonna use Velcro to attach a string to the tail and then that's gonna unattach it to Velcro. So for our motor, we're gonna use these pancake motors, these DC motors. They reach the size requirements that our design needs, and then we're gonna have two motors that are gonna connect to each one of our wheels. For our battery, we're gonna use one of these batteries, and we're gonna connect one battery to both of our wheels, and this battery can last for a very long time, and it reaches the size and weight requirements.
So to make this possible, we have to look at it from a programming aspect as well.
So we have to take into account the initial ejection method, which is something that we're going to have to run. And then after that, we're going to have to take a look at the initializing method. This part will entail getting communications with the lunar lander as well as deploying the tail, which is what we talked about earlier, how we have the connected tail that can deploy. So we've prioritized two missions. One is to go out, explore, and scan its surroundings. This will make use of a movement system, obstacle avoiding method, as well as obviously camera and photo taking. Our second mission will be to return back to our lunar lander, which will include the same obstacle avoiding method as well as camera and photo taking.
For our chosen prototype, we decided to go. For our chosen prototype, we decided to go with the deploy tail mechanism. Here's an early representation of our product.
So this is our CAD design. Our chiefs made it. It has our two DC motors in the inside, and it shows our unfixed tail coming out of our main chassis. We have a CAD representation of it that we could show you, but this is a newer one. But since we don't have enough time, we're just going to show you this one. And that's it.
So, yeah.
Okay. Do you guys have some of this printed out? Have you got some of your parts already?
So what we were trying to do is we were just gonna make the design a little bit bigger on CAD, like by a couple millimeters in every possible way, and then we're just gonna see if the things fit, and we're just gonna try to get one first moving vehicle. Also,
okay.
Parts, right? Next parts. We created this.
Okay, stop sharing so you can show us.
Out of Vex parts, we created this, which is a small representation of what we're going to have with our unfixed tail and our two wheels here. We're going to have a string attached to this, so when it goes flying, when it goes out of the ejector, we're going to have a string here holding it so that it's able to land straight and doesn't land over or in any weird orientation.
Okay. And what if it doesn't release? Is it supposed to release or not supposed to release?
When to get it out of our lander, we're just going to use a high force of speed just to get it out, and then we're going to attach the string to our tail by Velcro, and we think that our momentum is going to release the Velcro from the string.
Okay. All right. And so then it turns around and takes a picture of the lander as it's landing, right?
It's gonna eject, it's gonna drive around and take pictures of the land.
Okay. So its intention is to turn around and take a picture of the landing. So it gets ejected before it lands, and then it turns around and takes the picture. Is that okay?
It takes the picture at the end of as it returns back.
Yeah.
Okay, well, what we want it to do is to take a picture of the landing. So it gets kicked out before it's landed, and then it turns around and takes a picture of the lander as it comes down. Does that make sense?
Yeah.
Okay. And so are you guys planning on a Bluetooth back to your phone or something? Or
we haven't discussed
something simple like a Bluetooth would work. It's probably the simplest thing we can do just to establish a secure connection.
And that works fine. So, have you already decided on the type of camera that you were looking at on there, or what were you doing?
Something that can match like the size constraints and obviously the weight constraints. We haven't really looked into it yet, but we'll make sure to include those.
Okay. So you guys are on top of the driving mechanism, and so just be aware that camera is a pretty important component. Okay.
And the computer board. But what thoughts do you have there? I'm sorry, can you hear me?
Yeah.
So, are you guys thinking about using like an Arduino or a Raspberry Pi?
Yeah,
what kind of board are you planning on using?
Something that can fit within the tail of the robot.
Okay.
Yeah, so the tail is pretty important. So good. Do you have any questions for us?
We also have
a small CAD.
Oh yeah, we can see it.
So for So after landing,
Mhm.
is there like a computer mouse you could borrow?
Yeah, that's probably something you should have set yourself up with before,
Right.
but
And you can see the tail and how it deploys.
Yeah.
The animation that we have for it.
So the robot.
That's pretty much what our plan is.
So why are you putting the computer board in the tail and not in the main thing?
Just so, well, it'll be placed sort of horizontally so that it can fit. This spot right here will allow for the place for the camera, which will be pointing forwards.
Okay.
One of the things I said before is that we're gonna scale up our design a little bit and 3D print that. One of the main reasons we're doing that is to see where our certain parts are gonna go and if they're gonna be able to fit.
Yeah, that's an important thing. So did you have a question for us?
No. Well, I would highly recommend that you make some decisions on the board and the camera, the battery. Think about everything that goes inside so that you're actually providing enough interior volume to store all this stuff, right? And it's going to have to be secured. You need to think about how you're going to attach this, on the inside body of that. But again, a lot of it's going to be based upon, the material that you have to put inside and how much space it takes up. Mm-hmm. So the sooner you do that, the better for you.
Awesome. So yeah, that's true.
Are you guys worried about the dust getting on the computer chips or anything?
Well, it'll all be sort of sealed, so we hope that'll prevent any sort of.
I thought the tail opened up, and it looked like it was all open.
Be like some sort of protective layer over it.
Also, the tail will be more centered rearwards, so when it's moving forwards, the open bit will be on the rear, so it should help protect it against dust.
Well, the engine is blasting all of the lunar dust everywhere, so it's probably not. If there's anything open, dust will get in it. Does that make sense?
Prototype, we'll have to make sure that we can find a way to properly seal it.
Mm-hmm.
Okay, and it's not impossible. It's just something that you want to be thinking about, right?
Also, for our camera, there's certain very small cameras that you would use for like a colonoscopy or certain things like that. They need to be able to block some of the stuff that could come in its way without fogging up or just blocking the screen. So I was doing a little research a couple nights ago on something like that.
Oh, that is that's a unique thing because
and that's usually the housing, right? So whatever kind of housing that they have for that, I think would be a great idea. Mm-hmm. So good thinking. I like that.
Yeah.
All right, guys. Thank you very much. I know that we've got Tri-County kind of in queue at the moment. Fellas, thank you.
Thank you so much. Have a good weekend, everyone. Good work.
All right. I know that we've got another school that you need to speak to before our second set of students. So I'm going to step away and I'll rejoin you all when it's closer to those presentations.
Yes. Thank you so much.
All right.
All right. Tri-County, you are up. Thanks you for
Chris.
waiting. Yeah. Thanks. He's going to come back. He has more teams. After Tri-County. Hello, Tri-County.
Hello. Hi.
Hey, team. How are you doing?
Good. How are you?
Excellent.
You too. Are we sharing?
What are you guys going to tell us about?
We will be telling you guys about the lunar ejecting robot. Oh my God, guys, wait.
Well, we've heard that a couple times, so we do know your criteria and everything.
Yeah. Do you guys have a prototype?
No.
Okay.
We don't really have a prototype yet.
Yeah, we're still working on we have the motor we're gonna be using and
why
we have some code done, but
yeah. Outside of that, we don't actually have like a prototype.
Yep, we see it.
Yes.
All right. You ready for us?
Yes.
Yes.
Okay.
Hey, guys, can I just jump in real quick and make a comment to you? This becomes important to us in a few months, when you have your brochures that we're using, you have your last name's initial. Please put your full name down there.
Okay.
So we know who everybody is that we're dealing with. Okay.
Okay.
Thank you.
All right.
And your teacher's name, and put Miss Kristen, even though I know she's being at Johnson Space Center right now.
Yeah.
Yep. All right. This is our preliminary design review for the lunar ejection robot. Okay. We are from Tri-County in Franklin, Mass. I'm Charlie Whalen. I'm the project manager and note taker.
I'm Colin Flanagan. I'm the lead CAD designer.
I'm Joe McLaughlin. I'm the lead prototyper.
I'm Erin Campbell. I'm the corresponder and editor.
I'm Anthony Pryor Jr. I'm the corresponder, and I'm the other corresponder and also the accountant / purchaser.
And we're taught by Mrs. Magus, who obviously is in Johnson Space Center right now.
Yep.
All right, so our problem statement. NASA needs us to create a small, lightweight robot that can eject from the lander and travel autonomously on the moon up to 100 feet. And the robot also needs to be able to take pictures and transmit them back to an iPhone.
So, Glenn, did you change that 100 feet to 30 seconds?
No, I did not change it to 30 seconds.
So they still need to travel 100 feet.
Look, well, nobody's going to watch you drive it for 100 feet, but I'm also not going to say that it only has to live for 30 seconds, right? You need to turn around and take a picture, okay?
How about if we put it this way? At the CDR, you're not going to have a track or time to drive 100 feet.
Right.
But we want you to have documentation that it has, in fact, over time, traversed that much distance.
Okay.
Okay. So your testing stuff is important.
All right. Thank you.
Some of the most important design requirements are that it has to be under 15 ounces. It needs to also be able to transmit a photo and should be easily reproducible as well as easy to operate. It needs to be mobile in a sandy and rocky environment. It also needs to be able to operate on its own and should be able to function in lunar gravity and must be no larger than 4x5x6.
And that's not feet, that should be inches.
Yeah, you show it as feet. You use two marks to show inches. That's okay. Let's keep going.
Okay. So already created solutions. One, obviously the JAXA robot, which is on the slide. Another one is VidCastive R10, which is basically just a mini camera that can cast video feed directly to an application on your phone. And this would be perfect for being able to obviously transmit pictures from the bot. And another thing is DC motors, which are basically small, lightweight motors that can be used for the wheels. And this can help us keep the weight under the required 15 ounces.
Okay. I don't know if you guys can see me. I'm pretty off to the side, but so some of our initial ideas were to use large wheels so that no matter which way the robot lands when coming out of the launcher, to always be able to drive, wouldn't get like stuck on its back. Second idea was to use X-shaped wheels so it would traverse the ground better, step over rocks, stuff like that. And then spring-loaded ejection from the container so that the door would open and it basically just a spring would push the robot out.
These are some of the current ideas we're working with. This is a CAD model of the X-shaped wheels we were talking about before. This is our current setup. 2 DC motors with the Arduino Uno. This is we have it right here too. This is a SolidWorks model of the ejection box with we want to use a ramp on the inside so it can just roll out. And this is a Teflon tape, which is supposed to be dust resistant. So we want to use that to keep dust from entering the robot. These are some more CAD models. We didn't get a chance to print these yet, but this is supposed to hold our battery and our motors, and this is to hold. This is to attach the wheels to the motor.
What's the rectangular shape there for?
Oh, you mean the like the hole?
Yeah.
That's just we were gonna attach to the to our wheels from that.
Okay.
All right. So these are some videos of some testing that we did with Vex. So I can put in full screen.
Oh, look at that.
Wow.
I could slow it down too. Um,
Can you do that again?
yeah, I'm gonna do it right now. So it goes a bit off track, but that's like probably like 2 inch or 3 inch deep sand, and it seems to stay on top of it pretty well. And also the tail in the back helps it float above the sand a little bit. And then this next video right here, it's with like paddles, so they like kick up the sand a bit and move. That one, it kind of dug itself when we went backwards, so we're not sure if we're going to use that design. And then this third video right here, we have a little ejection box with Vex. And then we also have this little robot kit that we did with a camera attached to it that we hooked up to our phone. So we lowered the ramp with the Vex, and then you'll see in a second the robot drives out.
Oh, wow.
Very good.
Yeah.
Okay. So part of your thought is to have it drive out or you're going to use a spring to push it out. Is that right?
Well, we have a few different ideas. That was just a few weeks ago when we just built the box itself, and we just drove it out with that to show it that like the door can open and stuff. But yeah.
Excellent. Good. I'm glad you're looking at both of those options. Good thinking.
Yep,
I'm
and nice
impressed,
job
yeah.
taking the videos is important. And I kind of like the X because it would be way lighter than normal wheel.
Yeah.
Yeah, that was also part of it.
So
Now, those are pretty powerful motors you got there. Is that part of what's making it kick up so much dust, maybe?
Yeah, that was just with the Vex motors, but like right here we have the DC motors when we're gonna shrink the size down a lot, and we can also save weight there, but we could also program these to be faster, slower with more torque and stuff. So yeah.
Good idea.
So for the lunar environment, the moon has a similar surface to sand and fine gravel, and dust and sand could kick up into the joints or block the camera of the robot. There's also a lot of large craters that the robot could go into, but it shouldn't be a problem unless the lander lands very close to the edge of one. Low gravity will be beneficial for keeping the robot intact when it's falling, but it will also influence its driving and how far it goes out from the lander. The moon's surface can also vary from negative 250 degrees to positive 250 degrees Fahrenheit, which means that the robot needs to be very temperature resistant or has to be sent at an appropriate time.
So next steps and things we need to know, things that need to be known. Okay, so one, we're gonna test different types of launchers, just in case ours isn't necessarily the best. Two, we're testing the durability of the robot to ensure that it's able to maintain structure as well as just land right and also the weight. Another thing we will continue to work through trial and error as a team, just communicating properly and just making sure that everyone's ideas get out there and everything fits the requirements. Also, we will need to design something to keep the dust out of the wheels, which is just like the Teflon tape. That's a great way to keep the dust out of the wheels, the motors, just all that stuff. So it just doesn't, and also the camera, because we don't want the camera to be blurry or scratched up or anything while taking pictures and stuff like that. And also just finding a good camera, because we kind of have one, but it's not really the best. So we need to find a good one.
What kind of camera do you have now?
You know, off the top of your head?
I don't know. I can't think of the official.
Is it just big, or what's wrong with it that you don't like it?
I'm looking it up right now. It's called a Vidcaster R10. It's just a tiny little camera we found on Amazon.
Yeah, it's the camera that was.
It's like the size of a quarter.
Yeah, about.
And so, Mike, I don't have a preference for what quality of picture that we're talking about, right? Mostly, it's a task for you guys to complete. So if you've got a camera and it works, that's perfectly fine, unless you guys have some reason you want to cast away and get something different. Okay.
Yeah. So on the little kit robot that we have, I don't know if you can see it right here, but there's a little camera on here.
Sure.
I'm not sure what the name of it is though, but it works and stuff. The it's a bit blurry at like long distances and stuff, but for the most part, it works for now. But that's what we have so far.
Okay. And I see that also has some a motion sensor on there,
Yeah.
or a distance sensor. Is that so you can find the lander, or what are you guys thinking?
That just came with it. It is possible to program it to like it's like you said, find stuff, but we haven't explored that yet.
Okay. And part of what I'm talking about is after it lands, if it bounces or something like that, how is it going to know which direction to point so that it can get a picture of the landing?
Yeah, that's a good idea.
Just as a thought, another option might be, there's hot plumes coming out of this engine. You could use an infrared sensor, or you've got a breeze coming off of it. Maybe it can point itself into that direction. So just some other thoughts for you. Okay.
Yeah, like some sort of thermal camera or something.
Sure.
Okay.
You can also have a transmitter in your box, and now it turns around and just finds the transmitter.
That's a good idea. Thank you.
Sure.
So we have
question number one. Yes, you can make video or photos. I don't have a preference.
Okay.
So you gave us that link or the person to help us with the coding, but do you know of any other good videos or even what type of coding language you would recommend us learning?
So you might check out if you go to SparkFun, they have coding for just about every piece of hardware that they have, and if you pick up Arduino or Raspberry Pi, they might have coding for all of those devices.
And they have tutorials. SparkFun does too. But ask your questions to Michael Frank at RIT. They're more than willing to help you.
Oh, that's good.
Yeah. So we were looking at the design requirements for the box, and it said that the box didn't add to the weight of the robot. But is there still any weight that we should keep the opening mechanism under, or the launching mechanism under?
No, but keep it simple, right? The simpler it is, the more likely it's going to work. Okay.
And is the opening allowed to be outside the box? Like, can anything be on the outside? Is obviously as long as it would survive space, I guess you could say.
Right. So you guys, if this is your box, right, and this is your door, or however pin or something that's going to hold it in place. If pretend you've got a spring inside, so that your thing is pushed up against the wall. All you have to do, your finger is your action, right? If you flip that switch and it opens, that's perfectly fine as long as you are not pushing the robot out. Does that make sense? So your finger can be that first action. Okay.
This last one, I think you guys already gave us an answer to it earlier throughout the presentation. So.
Right. It does not need to move in any particular direction. You guys can decide how you're going to point towards the lander. Okay.
Thank you.
All right.
Thank you.
That's it.
Any other thoughts? Dave, you got some thoughts for him?
I just want to compliment this team on the fact that you have actually built something and started testing. You understand the most important part of any of these projects. They don't become real until they move off a computer screen into something that actually functions. And I got to give you a lot of credit there. I like what you come up with, right? I think that simple 4-spoke wheel concept is brilliant. I think you're on the right track, so I encourage you to keep going.
Thank you.
Yeah, I totally agree. That, and you did a great job taking videos of everything, which is your
I love
data.
your video.
Yeah, that really was great.
Yeah.
Awesome.
And again, let me just add, back to that notion of, can you drive 100 feet? You'll have documentation of that, right?
Yes.
You'll be able to show over a long period of testing that this thing has actually accumulated 100 feet of distance in your testing. And that's plenty right there.
Yeah.
That's right. So, tell me about, so you've got those yellow motors. They have a lot more speed variation. Do they have enough torque to be able to handle the X-shaped wheels that you've got?
Well, we haven't had a lot of chances to test it yet because we just finished making the CAD model. We're still working on printing it.
Our wheels, we printed them yesterday, but we messed up a little bit with the 3D printer. So
yeah, we need to work on the measurements, but we're pretty sure of it.
Okay.
Yeah.
And I will too. I don't know how because there's a lot of gearing with that, but it's not about being fast. It's about getting the job done.
Yeah.
And so I think you guys are on a really good path. Good job, team.
Very nice. Nicely done. Any questions, email them to me, okay? And copy your teacher now. Thank her for stepping in for Mrs. Magnus too. That's awesome.
Yeah.
All right. So have a great weekend. And is the other team ready?
Yeah,
they're right there.
Oh, awesome.
All right.
Let's hear
Thank
from
you.
them.
Yeah.
Thank you so much.
Jack.
Enjoy your weekend.
Guys, so did I do it wrong?
No, they're just saying like I was saying it has enough torque.
Oh.
First team has to stop sharing their PowerPoint. Thank you.
Make sure I see everyone.
Good morning.
Good morning.
This one.
It's trying to connect.
We see it.
Yeah. It's just trying to connect right now.
Yeah.
Yeah, refresh.
Refresh. I can't press the refresh button.
Yeah. Top left.
I like you put down both teachers.
There we go.
Yep, it's loading. Yeah, perfect.
So this is our preliminary design review. I'm Jamie.
I'm Dom.
I'm Connor.
And that's James.
Our instructors is Miss Magus and Miss Bat. We're from Tri-County Regional Vocational Technical High School. Long name.
All right.
So I am the corresponder and purchaser. Dom is the lead prototyper and editor. Connor is the project manager and scheduler. And James is the lead CAD designer and note taker.
So the problem statement for our project: how do we, as engineering consultants for NASA, design, prototype, and test a functional lunar ejecting robot that can eject 2 to 3 feet from a lunar lander, move 100 feet along the moon's surface, operate autonomously for at least an hour, take photos of its surroundings, and upload them back to the lander?
The customer needs
So what NASA needs is a robot that will be able to survive a 6 foot fall on the moon. It needs to be relatively small, like under 15 ounces, and it needs to be able to fit into a 4 by 6 inch by 5 inch box uh, prior to ejection. And it also has to have battery life that'll last at least an hour and a method of locomotion that'll travel 100 feet before it dies.
So some of the HUNCH resources we really studied were this graph here showing how the robot is actually going to eject from our box. So side A, from what we can see, is where it's going to eject, and it's going to eject when the actual box is 6 feet from the ground, and it must land 2 to 3 feet away from the lander.
So the lunar environment, the temperature ranges from above 250 degrees Fahrenheit to below 200 degrees Fahrenheit. The gravity, the acceleration due to gravity is about 16% of that on Earth. And the moon surface is mostly powdery dust and rock debris.
So for our list of most important requirements, we figured the size was most important as it can't exceed the 4 by 6 by 5 inch area. The weight was definitely also pretty important. It can't exceed a weight of 15 ounces. The camera and its upload is basically the whole project. The survival of the robot must survive the 6 foot drop into sand. The robot must travel for no less than an hour. It must be able to travel up to 100 feet, must be able to easily be able to reproduce, and the robot must eject between 2 to 3 feet from the lander. So for our existing solutions, there's the JAXA robot. The robot designed by JAXA provided a pretty sound base for the project with a diameter of 8 centimeters and it weighs about 9 ounces. The locomotion method is a bit strange, but it's something we could look into in the future. And this AC bot, it was a robot created to traverse the desert, and it's our inspiration for our current paddle design. The plastic shells are a pretty common solution for keeping out the dust, and it seems to be a pretty lightweight and effective solution.
So in order to make decisions on numerous of our ideas, we've created decision matrices that you can see now. So we made one for different materials. We made microcontrollers, locomotion, and motors. So the green is basically what we're focusing on actually incorporating into our prototypes. And then you see the yellow highlighted things are kind of our backup options. And then the red, we tried it and we didn't really like it. For like the Raspberry Pi, for example.
So some of our current ideas for locomotion, as of right now, we're most focused on paddles, but we have tried other methods of locomotion that you'll see later in the presentation. We have videos of some other methods of locomotion we tried. And the ones we tried was, we tried using treads and we tried using wheels, but we found that wheels aren't the best because they can very easily get, there's not a lot of traction for the wheels. And they're also kind of bulky. And treads, they have a bit more traction, but they're also even bigger and they're even heavier. So right now we're working with paddles.
So for materials, something like aluminum is pretty easy to use. It's very lightweight, easy to machine and work with. ABS was definitely our best 3D printing material. That's what we're going to use for our prototyping moving forward. The DC motors, which are currently on our 2 prototypes, are very effective and powerful, and sometimes they lack the torque we need, but as of right now, we have them working and functioning. And watch batteries, which are on one of our prototypes, are definitely something that work well. They're lightweight and long-lasting, and they have the power we need to move the paddles.
So for using the camera and uploading, currently we're using the ESP32 cam, this one right here. So far, it seems to be the best one we could find because it's very lightweight. It's only 10 grams, and it has some onboard capabilities for sending the pictures and videos it takes off of it to where maybe the lunar landing.
So how will we test? We're gonna test that we can take photos from the camera and send them to our phone here on Earth. We can also test how long the batteries will last while running the motor, and test different types of locomotion as we have. Continue testing to drop testing, making sure that it will survive a fall, and test different types of ways from preventing sand to get in the joints.
So our next steps are to continue designing these prototypes and improving them in CAD, and then actually constructing these rough prototypes. And we're going to continue testing from the previous slide and expand upon our ejection systems. We're going to model and test those pretty soon.
So some of our tests that we've done, we started with wheels, and it looked like it did pretty well on flat surfaces, but when it hit a hill, it kind of got stuck, and the wheels started slipping. Then we did these cams and followers, and they didn't work at all. They couldn't move. We did treads, and it worked pretty well. Had a little bit of problems on hills. Then we moved to our current design, which is paddles. And our first problem was one of the axles was longer than the other, so it started going in circles. And then we fixed that, and it got to this, and it seemed like it worked the best.
That is impressive.
Yeah.
I love that.
Okay.
So we made a few CAD models for what's on the project. If we look on our actual prototype, what's connecting the axle to the axle from the DC motor is we designed an axle adapter. You can kind of see that. It fits onto our paddles and also clicks right onto the DC motor. We have two different kinds of chassis. This one holds a 9-volt battery and clips right onto the motor. And this one holds 2 watch batteries, an Arduino Nano, and the camera, and also clips onto the battery. And then last is the design for the paddles. It's a pretty simple design, just 2 curves, and it's been pretty effective so far. We might need to revise it in the future, but it's worked well for us.
So for the ejection system, we don't have much in the way of models right now, but we just did some math just recently to try and figure out what sort of force we need to send it the 2 to 3 feet, because we figured it might be more than we're expecting. And we did the math out, and it turns out we need to eject the robot either between 0.41 meters per second and 0.61 meters per second. Are these some questions we have for you? Are there any methods of ejection you prefer us not to use?
No detonations. Keep it simple.
Yeah, keeping it simple is good. Although explosions are fun.
Cool.
Do you suggest to keep a robot straight?
Stable,
straight.
When you say straight, clarify that.
So when the robot's going forward, sometimes we've had issues with it turning, going in circles, and we'd like to keep it more straight if possible. Is the thing.
What do you think is causing it to go in circles? Is it just a difference in friction from one side to the other?
It could be that. It could be just the length of our axle.
There's a lot of things. We're not.
Oh, I can see that.
Yeah.
Okay.
The other one is, how often should the pictures be taken?
How often is up to you. I mean, if you want to take continuous video, that's okay. If you want to take still shots at given time frames, I'm okay with that as well. Going back on the previous question, so right now, are you using one motor or 2 motors? I mean, how do you turn? How do you choose which way to go?
Currently, we're only using 1 motor, but the motor has an axle going through it, so there's one axle going through it spinning at the same rate. So it's just 1 motor right now.
Okay.
I think that might be part of your answer. I think that you're probably going to have to go, because you're just a 2-wheeled vehicle, you may end up having to have 2 motors that you can drive at different rates to be able to make it turn or go straight the way you need. Does that make sense?
Yeah.
Another option could be like a tiller, right? Meaning, like on a boat, you've got one motor, and then you have like a tiller that drags behind, and you can choose what direction you curve it. Does that make sense?
Yeah. Another question we have is the goal to take pictures of the lander as it's landing, or just the moon in general?
Well, the first objective is to take a picture of the landing. But of course, afterwards, we'd like to get any other pictures that we can.
Yeah.
Right. And then, does the robot have to turn, or could we just use multiple cameras, like front and back, or a pivot?
Oh, yes. Yeah.
Yeah, you can use multiple cameras, and you can turn and go straight. It is up to you guys as to how you want to do it.
Okay. Well, but when you think about at the critical design review, when you're demonstrating the functionality of your robot, you're going to put your ejection box in your robot on a tower that's 6 feet above the surface it's going to land on. It's going to eject into essentially something like a small plastic kiddie wading pool with sand infill, right? That pool area is going to have about a 3-foot diameter, right? It's your target zone, if you will. Okay. So that area is not that big. If you're driving in a straight line, you're only probably going to go about, 18 inches and that's it. So you're going to need to be able to turn this. Does that make sense?
Yeah.
Also, if you're just using one camera, the camera needs to be pointed in the direction of the lander. And when this ejects, you're not quite sure what orientation it's going to land. So it may have to turn itself around, hypothetically. Do you understand? So from that standpoint, it really does need to be able to travel in more than just a straight line.
Good comment.
And that goes back to that idea of having a differential on those paddles so that you can accomplish that goal. I suspect you're going to end up going with 2 motors.
Mm-hmm.
All right.
Right.
Or yeah. If you guys have any questions you guys want to ask as well. If not, we're just going to show off the prototypes we have right now.
We'd like to see that.
All
Stop sharing.
Yeah.
Which one do you want to do first?
Let's go with the 9-volt, because the 9-volt's kind of worse.
Yeah. You want to explain what it is first?
So, not really.
All right. So, well, to start off, we have this design. We only have one camera right now, but the camera would be placed right here. It uses the 9-volt battery as power, and right now we don't have the Arduino attached. But it's a relatively simple design. It's small, it's compact, but this is more of like a secondary design. The other design is probably our main one. If you want to run it.
It's gonna go a bit fast though, because we don't have we're gonna use a resistor on it, but we've just been testing, going through them to find which resistor would be the best, and we haven't quite figured that out, so we don't have it on there. But it goes a bit crazy.
Just go to the other one.
Yeah,
the other one's good.
It goes a bit crazy.
All right, so this is our current design here. So we have, if you can see there, we have 2 watch batteries being held in this indent right there. This is the current camera we have here, the ESP32.
Oh, I see. And this one's going to turn to the left, isn't it?
Yeah,
it goes kind of straight.
It goes pretty straight. Yeah.
Does it? Okay. Keep going. I was just looking at the distance there.
We want to test it.
Yeah.
So this one goes at a pretty good speed. It doesn't go crazy fast like the other one. Is pretty controllable. The current issue that we're looking into is trying to make like a fin or something at the back to keep it straight, keep it grounded, because it front does kind of tend to stick up, as you can see when it does run.
Now, I also see that your two paddles are going at the same. They're both making contact at the same time. Is there a reason why you've chosen that? Is there a reason why it might be better a different way?
As of right now, it's all we've tested, but it's been efficient so far. But we're definitely looking into switching to 2 motors, having them move at different speeds, and we're going to see what's more efficient in the future.
Okay, and what I'm thinking is, you could have left, right, kind of hitting, and I don't know what it does. It's more of a question.
If you don't mind, we're gonna have the camera take a picture. We're just
let's see it.
It may work. It's 6 volts. 6 volts should be.
So guys,
don't burn it out.
While you're doing that, can I ask, what are your thoughts? Are you going to build a housing? To cover everything.
Yeah. This is just so we can so we can access everything. So it's a lot more modular. So it's just prototyping right now.
I understood.
This might be a bit bright. I'm not sure. We'll take a picture.
Reset.
Is it gonna? No problem. It may not work.
Okay.
The power supply we were going to use isn't working right now, so
okay.
We're just having some issues.
So, were you going to send it to one of your phones?
Currently, we have it taking a picture and mapping it onto this SD card.
Okay.
There is another way we have it working with a web server. So it accesses the Wi-Fi and it'll stream a video to a website that you can access. But we don't have access to that right.
Very good.
We're just struggling with that right now because it's we don't have the Wi-Fi right now. That's just the problem.
Okay. Well, and think of it, there's not going to be any Wi-Fi on the moon.
Yeah.
So you want to be able to send it directly to a phone if possible. Does that make sense?
Yeah. We've been working on that as well.
Okay. That sounds great. I love that you've got you guys are coming a long ways. I think that looks terrific. Excellent job, team. Keep this up.
Absolutely.
I like your testing. Yeah, really nicely done.
Thank you.
Thank you so much, team. And you have a wonderful weekend.
You too.
And send me questions whenever you have any.
Yes, yeah.
Okay, great job.
All right, thank
you.
Thank you.
Thank you, Miss Bat, for us too, for continually helping. Oh, there you are. Thank you so much. I appreciate that.
You're doing great. Thank you so much for helping out.
Yeah. Just stepped right in. All right. So we're going to go back to Half Hollow. And I see they're on.
We're still in that ideation phase. So, okay. We've got 2 landing leg teams that are going to be coming in to chat with you now. We're going to share over their slide decks. We don't have quite the amount of prototyping that you've just seen from the other schools. So,
that's okay.
A lot of ideas and research at the moment. But, still good stuff.
Yeah.
Excellent.
All right. Can you see their screen okay?
It's coming on. It looks perfect. It looks like it's going to be perfect. It's loading.
All right, beautiful. Here we go.
Yes, perfect.
All right. So I'll let you guys take it away. I'm going to bring the computer a little closer to you so you could control it.
Is everyone in view?
Don't worry about you being in view right now. You look great, but they want to see your work right now.
Okay.
All right.
How do we go to the next
So you
slide?
could just hit the space bar.
Space bar?
Are we not able to?
No.
This was happening to us before for whatever reason. Let's see.
Yep. Yep. We see you again.
All good? Yeah.
Yes.
So we heard that we should skip over or gloss over the problem and constraints. Is that okay? And just go
Sure.
straight.
That would be great.
All right. So our research said that we should use 4 legs because it'll be ideal for an unlevel ground. And a way to absorb the shock would be the use of sponges. And we thought sponges would be a great idea because it's cheap, reusable, and lightweight, and it can also act as a crumple point. Or we could also incorporate springs because it's also lightweight, cheap, and reusable. It can also gradually decrease the acceleration upon the landing. And our research also showed that we should use angled supports to distribute the weight upon the legs.
So to like further our research, we used a decision matrix where we had 6 ideas. As you can see, we had 3D printed legs, hydraulic absorbers, using 3 legs instead of 4, using springs, metal legs, and then using crumple points in our legs. So while most of these had a near equal total point count, we were able to rule out idea 2 and 3. And now we are currently implementing idea 4 and 6, which are using springs, and crumple points, which we'll use a sponge for. However, we might re-implement idea 2 to control the recoil of the spring. And so this is our first sketch. It uses a lot of metal for the legs, and it's very complicated, and there's a lot of potential breaking points. So, and this would use 4 legs, and you would move on from this. So this is our next sketch, which is pretty close to our current CAD design, which has the leg would angle inward to the center to support the weight better. As shown from our research, it would have a sponge, as you can see here, to act as the crumple point, and it would have a spring to slow the deceleration of the drop. So this is our first CAD design. So there's a wide trapezoidal base to support the weight better, and then the yellow sponge on top of that to absorb the shock and mitigate the effect of the tilt. And then there's an angled connector that's either metal or 3D printed with an angle of 14 degrees to distribute the weight of the payload between the 4 legs better. And then on top of that, there's a spring with a spring core inside it. So this is an area of uncertainty and further discussion, since we are currently deciding between using like a spring in a piston mechanism or like back to the hydraulic or some other kind of absorber to absorb the shock.
So to add on to the lunar landing legs design, I plan to add a metal cylinder called the piston spring cylinder. It is composed with a spring inside it and a rod too. So the rod pushes the spring and it absorbs the impact. The guiding systems make sure the rod stays in place during the process, and the sealing system compresses the spring. But there are also problems we need to consider, such as the cost and spring recoil. And the materials we're thinking about adding is stainless steel for durability and Inconel. So inside of the design, spring should be on top of the rod, and the rod on the bottom should compress the spring and absorb the shock. It allows for reusability as the spring can go back to its predetermined state. And it's really effective for cushioning the landing. So as you can see, this is the full design and the location of where we plan to put it.
Right. So this is the payload and delivery part, right? And this again is the problems and everything that we're just going to go skip those. So onto the research. And so this is part of the release process. So we were thinking that we could use tab clips. I'm going to get into that on the next slide. And to release it, and to use RCS thrusters on the side to help gradually bring it down from ejection. So My inspiration from this is my vacuum cleaner because when I vacuum, it goes into a storage, and I guess the payload is like a storage, and the vacuum is like the rocket, and you can detach the bag from the vacuum just like detaching the payload from the rocket. And I like this idea because it's super simple, really easy. All you got to do is pull and release, and it's off. And then to put it back on, you just put it and then do the opposite of what you did to take it off. So I liked it so much. And so this is very, very early sketching and designing of the clips and the hooks. Um, I like the 3 points on the hook because it on the base. So there's 2 points on the base that allow two arms that connect to the hook to move, and the hook would also have a point where it can also move as well. Um, and that would lock into the other hook that would be stationary. Um, so this is my CAD modeling, and I used the can as base of reference point, so it helped me see everything easier. So to the top left is the base, right? The base of where the hook will be. So the base is connected to the can. It has legs that connect to the hook base, the actual hook that will connect to the other one. Um, and the bottom left is the full thing, and the actual part it's going to clip onto. And the part it's going to clip onto will be stationary from onto the bottom of the rocket. And I color coordinate it on the bottom right so it can be easily seen. Um, the blue will be connected to the rocket, and then the red is connected to the payload. And yeah, so this is my link to the design and onto the actual part so it isn't going to crash down and break the thrusters. And again, the problems and criteria, I'm just going to go over that. And so our research is we're going to use cold rockets. So the actual air or substance that comes out of it is going to be CO2 canisters, like from an airsoft gun. And we're going to connect those to the payload, and it has to be the thrust to weight rate ratio needs to be achieved. And we took our inspiration from SpaceX, the SpaceX Falcon, and the Perseverance rover Sky Crane. Is very early concept generation. To the very top right, there is the side of the payload and the CO2 canister. And to the bottom below that is some simple coding. I did not make the coding. It is the Jerry Wu and Joseph. They made that. And to the top right, or myself, sorry, to the top left is the valves for the actual releasing of, so all the substance comes out evenly. And below that is, again, the same thing from the top right. So this is how we're going to hold everything in place, right?
Okay.
So,
let me ask you, so you've landed and now you're going to use thrusters to lift up your payload?
no, this is when we're releasing, we want the thrusters to be able to help gradually bring it down so it doesn't crash on landing and break potentially.
How far are you planning to cushion them with these thrusters? What kind of distance is it falling?
So right now it is falling 8 inches, and we're going to try that out. And if it works, then that's great, and we'll go on to bigger, larger heights. And if it doesn't work,
hold on. The whole rocket is dropping 8 inches, right?
Yeah.
And then once you've landed from that 8-inch drop, now your can is only going to be less than an inch from the ground. how much more do you want to? I'm not sure how far you need to lift this thing.
That's a good point. We're gonna look into that more.
Okay.
But
Okay, continue with what you've got. Tell me more.
So to actually mount the thrusters, you can't just glue them on. So we were thinking of on the left, like I call it a canyon design because the two extrusions on the left and the right you can easily fit the canister right in between and maybe put some resin or silicone resin. And below that is concept nozzle for it, gearbox. This is how everything's gonna be released. How we're gonna get everything out. Um, and then to the right again is different angles of the nozzle and the motor. We're thinking of using sensors to like motion sensors. So when you put it at a certain angle, then it'll release. So you start from the side, maybe, and then everything else is just different angles of everything. Right. And these are just simple nozzles, everything you can find off Amazon. Yeah. And this is more of the coding. The gyro degree reading. So when it leans, it'll open or close the valve, and when it leans again, it'll open or close it again. And here's the concept generation of the thrusters, and to the bottom right is the CAD link. So the two canyons, as I call them, hold in the actual canister. Below the canister is the gearbox, and next to the gearbox, the gray block is how it gets released, how you release the CO2. And that's it.
All right, stop the share.
How do I stop?
Red button.
The red button.
How many canisters of CO2 are you thinking of using?
4.
4. Okay. So this is a can of beans. I think you're going to shoot it up to the ceiling.
No. So we're thinking of using an equal amount of cans to the same amount of legs.
Okay. Oh, well, okay. So wait a minute. You've got a total of 4 cans, 2 of which are empty.
Yeah.
And so if you put one canister of CO2 on there, you're going to shoot it across the room, I think, aren't you?
I didn't think of that. Maybe you have a good point. We should.
Yeah. Can we back up for a minute and fundamentally, why do you need these canisters in the first place? When you stay with me for a second, your entire rocket is going to be dropped from a height of 200 millimeters. Let's just call that 8 inches, right? And it's going to land on the surface, at which point you're now releasing the payload. The payload is a can of baked beans. So the distance it has to travel from the body of the rocket to the ground is actually primarily determined by how long your legs are.
Yeah.
Right? When you think about it, if you design the legs and you have to account for, some compression when this lands, etc., you're still talking a distance of probably 1 inch or less that the can is going to drop from the rocket to the ground, right? You don't need to control that much. You're over engineering this way too much for what you need to accomplish here. I think your release mechanism has a lot of potential to it, And I would continue to, and I would encourage you to continue to work on that. But the other things of like adding thrusters, etc., just let that stuff go. You don't need that, right? Let me ask you a question. Have you purchased the body of the rocket? Do you have 2 cans of beans and 2 cans of diced tomatoes?
No.
Okay. First things first, go get those, right? Once you've got those together, you're going to kind of get a grasp on how much weight you're going to be dropping from 8 inches. That's going to tell you how robust your legs need to be, etc. And you're also going to get a sense of, that bottom can in height is probably, I'm guessing, what, Glenn, 4 inches, right? There's not that much to it. So I just don't want you guys to try to, theoretically over-engineer this stuff. Go get the materials and take some duct tape, tape those top 3 cans together just so that you kind of got a body of a rocket. With that bottom can, you can attach it somehow with a couple of strips of tape or something and get a sense of what you're doing. In reality, I suspect that once this thing hits the surface and stabilizes and you're ready to release that can, you're going to be dropping it the equivalent of about a 1/2 inch. That's all. Okay?
Yeah, that was very good, both of you, to explain that. And also 3D print the part that you're not just dropping the can, but you're also dropping a little vehicle. So 3D print that vehicle, and Glenn gives you all the dimensions for it. And there is engines for the top of the can, for the very top of the rocket. Glenn, do you have those 3D printed things?
I don't have them printed, but I do. So here, I'm going to take this off so you can see it. Okay, so there's my last can. This is the can that you're going to drop, and you're only trying to drop it, depending on the length of your legs, it might be dropping it that far. So what I'm thinking about, one, I really like your attachment mechanism.
Yeah.
So you are going to have 2 clips on the side. I think that's really smart. I think that's a really simple method. How are you going to release that, right? So if you pull over, if you pull that lever over, and I've got the same kind of attachment on my
vacuum.
What do you call on my vacuum cleaner as well. I think that's a really smart thought. So this one you can't put any holes in, but this one you can. And so it might be that you choose the latch to be on this side and the other mechanism on this one, so that when you flip this, it just falls. Does that make sense?
Mm-hmm. And maybe so you could even maybe have when the legs are in place, then it somehow releases the mechanism to release the can.
And I'm okay with that as well. It could be, as your legs come down, you've got that spring mechanism on it. What if it pushed on the release mechanism and it dropped the can from there?
Yeah.
So these are just thoughts for you in terms of how you want to do it. And if it's going to fall 2 inches or more, then yeah, you need to think about, I don't want to damage all my computers because they've fallen a long ways, right? But the idea is if it's a short distance, you can drop it. But if it's a longer distance, then you might want to have something like a cable system that could drop it down a little bit. Right. Does that make sense?
Yes. Yes.
All right.
Okay.
That's awesome input, guys. Thank you for visualizing that for them, Glenn, because I don't think that they were looking at it. And Dave also, just that whole keep it simple principle is definitely something we've been trying to ingrain in the fellas, but hearing from another voice will certainly help that along. All right, guys. Thanks.
Can I make one quick suggestion?
Yes.
If you have those 4 cans together, even before you get your legs completely assembled, you can attach something, even some cardboard, to kind of represent the legs. And then if you have the weight distribution, 2 cans empty, 2 cans full, etc., just start dropping it, right? Maybe have somebody with a cell phone that's videotaping this so that you kind of get a sense of how much force you're actually impacting when you hit the surface. That's going to give you some sense of how much cushion you need to build into all of this. And it will probably influence your design ideas a lot. Okay?
Yes.
All right.
Awesome. Thank you so much for your work on that. Keep it simple and have a wonderful weekend. Thank you.
All right, fellas, thank you. I'm going to transition into our other team, so you guys can head back to class. Good have your passes from earlier. All right, and ladies, we're going to bring you on in.
This is a cosmic dust.
Nope, this is still our second, because I think you blocked the half hour for legs.
Yeah.
Because there were 2 of them. We're going to start with not sharing our screen, because I think there's a couple of simple prototypes they want to show you first.
Good.
And then I'll send them into their slide deck.
Yeah, I did give you 2 for the.
Oh, you're
Hey, ladies, how are you doing?
higher than that.
Hi.
Introduce yourselves first.
Hi, I'm Holly Towers. I'm the hair Kara. Hi, I'm Lauren Jen. How are you guys doing?
Good.
Excellent.
Nice to see you.
Nice to see you too. So we have made prototypes for our lunar lander legs, and basically they function kind of like a bike shock on a mountain bike. And basically, when the lander is landing and it hits the surface of the moon, it's gonna first hit our little shoe, as we like to call it, for our bike shock functioning legs. So our shoe can come off, and right now we have it out of air dry clay, but for the final, we plan to make it out of a heat resistant silicone, so that it can absorb the initial impact of our lander landing on the moon. And then we have our bike shock functioning legs that will hit the moon and absorb the remainder of the impact, that have also a lock function. This is used as a compression spring to help absorb the impact, and it has kind of a lock mechanism, so it won't come off. And that's our legs. And then do you want to do?
Excellent, ladies. I like that a lot.
Absolutely.
For the payload, we were thinking about like a spool mechanism where it will like slowly drop down. And right now I'm using a compass, which like to use a compass, it like goes around like a CD. So that's where we got an idea from, like a CD player where it like goes around. So it goes around, and because of the microgravity in space and in the moon, the package won't drop like wildly or like unsafely, but because of the microgravity, when it goes down, and it'll go like more slowly, and the CD like mechanism will just make it go around and drop, and it can also go back down.
Very good, ladies. So, so right now you've got a big roll of string. What do you plan to move to when you get into like, the steel cans and stuff?
We planned to cut a hole. Okay, so all of our prototypes are very upscaled so that it would be easier to show and demonstrate how they work. So this spool is going to go inside of the top of the cans and gonna drop the package down. And then our legs are gonna surround sort of a hole on the bottom of the can so that the package can drop out.
Do you have any sketches or CAD stuff you want to show them in the slide
I
deck?
think it's
Okay, we'll get you over to the slide deck then.
Okay. Good job, ladies. I like what you're doing. Very smart.
And it was nice and simple too.
Absolutely.
Just Google meeting Google. Give it a
Yeah.
second.
Thank you, Mr. Regini. So this is kind of just a more involved like demonstration of how we came to our ideas. We thought about bike shocks because we knew that it was going to absorb shock of the initial landing, and the silicone was just to kind of help the landing and make sure that the rocket didn't fall over because of the tilt of the moon surface when we landed.
And then the spool system, we originally thought of gears and like little mechanics that could like you have a string in between and similar like the spool like would bring the package down. But we got our ideas from like a CD player and like Mr. Regini that we should use a spool instead to minimize the damage like the dust in the moon can do. So we like resorted to the spool system instead.
Okay.
This was our original sketch that we made on a whiteboard. This was kind of as we were transitioning from our pulley system with the gears to our spool design that was going to go at the top of the rocket. We switched to the spool design because the gears had like lots of room for error because it was more moving parts and more mechanics that we would have to work out, and also dust and debris can get inside the gears and mess up the mechanics of the package dropping. This was our final sketch for our lunar lander, and in this sketch you can kind of see how at the bottom of our lander in the top left corner of the page you can see the thick line on the bottom.
Direct them with the little mouse too.
Oh my gosh, I can. Okay, so this is kind of a hollow part of the rocket where the package is gonna drop down from there, with the spool at the top and then the 4 lander legs at the bottom.
So these are just like some like further research and plans that we had for it. Like we wanted to take it into account like how heavy the like what we were transporting would be and how we would like get like the weight distributed evenly so nothing like tilts or falls. All right, next slide.
No, just read here. It's the attachment. Oh wait. Oh
Yeah,
yeah.
that's
the,
right.
this attachment. Is it? I can't see it. Oh, but we can't see like the.
Can we move this?
Yeah. Sorry.
Okay,
Yeah. So we don't.
Yeah, so we would just think. We also wanted to like think about where we would place the bike shock, so it'd be where it would be most efficient and where it would like absorb the most energy, the most impact from. Sorry.
And that's it. That's sort of how far we've thought of as of.
Excellent job, ladies. I like your demonstrations as well. I think that's really smart.
Absolutely.
One thought I had for you is, okay, so here's the size can that you're looking for, right? And you want to put a spool inside here and then a hole through the bottom, right? I think that's a great idea. I think that's a great path. You could possibly, I don't know if it makes sense to you, you could do 2 threads going through so that you're not just holding it in one place, you're holding it in 2. Does that make sense? And both of them could come off of the same spool. Does that make sense?
Yeah.
They just go in opposite directions or something. Okay? Excellent job, ladies. Now, the other thought I had for you is that instead of having the legs, let's see, you can set up your legs any way you want. I had thought of it as the legs attaching to this as well. But you had shown it like the legs were attached way down here, and then this was dropping down in between. If you guys want to make your legs so that they do that, that's perfectly fine. Okay. Do try to keep. I'm not worried about the size or the weight or anything like that. That's all something that that your team can decide. Okay. As much as I would like this to look like everything is scaled according to the size of the rocket, that's not a reality because there's just no way for you to make the spool and the motors and the springs and everything like that. That's not going to work out for the size when you scale that up to the big rocket. So I really want to see your ideas more than I want to see trying to scale it and make it fit the size of the rocket. Does that make sense? So you guys keep doing everything the way you got it. I think that's really smart. Okay.
Agreed.
Dave, you got any thoughts for him?
No, I did that. You covered it there. I'm impressed with what you've done so far. You're moving in the right direction.
And I really liked your shoes because that made it flexible. So when it lands, if it hits a rock or pebbles or stuff, it would just absorb that into the design of the shoe. So that was really cool too. And definitely I would use 2 strings because one would slow it down, but it wouldn't keep it necessarily straight. 2 points determine a line, and that would help it stay level.
Thank you.
Thank you.
All right.
Okay.
All right, thank you so much, ladies. Did you have any questions?
I don't think we had any.
No, I think you answered a lot of our questions.
Okay, just contact me if you have any questions. Nice job. Enjoy the weekend. I like the bike shock absorbers, the mountain bikes.
All right, we've got our final team. We've got a dust removal.
Cosmic dust, yep.
Cosmic dust.
I can't wait. Hey, Flo, we still have more teams today, correct?
We have Glenelg next, 1 team, then Tri-County, and then Glenelg, 1 more team. So 3 more teams.
Oh, okay. That sounds great. Thank you.
Yeah, and we don't have the Frontier teams. So we just have 3
how
more.
come?
They couldn't make it. The teacher couldn't get to school today. So, and Nancy's going to have them later on.
Okay. All right. We will work that.
Yeah.
Whenever your team is ready, we are ready for you.
Hello, I'm Nick Torrey, and this is
I'm Ethan Jaloski.
and we are Team Dreams. And the goal of our mission is to collect the cosmic dust off of the International Space Station exterior, and get it into an airtight container for sampling.
The criteria of our mechanism.
Sorry, please. Let's skip over criteria and constraints just for the sake of time because they're well versed on that stuff, and let's go into more like your research and your prototyping.
Okay, perfect. So,
all right. So we started off with our first idea was trying to like dismantle a Roomba vacuum, and then and then we were gonna try and use it as like a street sweeper to sweep the dust into a containment center and make it airtight in there. But we thought that would damage the ISS because some of the cosmic dust is made out of quartz. And then we went down to a static vacuum to try and pick the dust off of the ISS and try and like connect and try and stick it onto a piece of
nylon. Yeah, we could do the differential and static charge. A bunch. If a dust particle is charged a certain way, it would attract to the nylon. But then we also realized that that could be problematic because not all the particles might be charged the same way.
And finally, we went to an oscillating device where it could try and vibrate the dust off of the ISS to try and collect it into a collection space.
So we don't plan on using any ready-to-buy mechanics in our collector, but we do plan on modifying ideas from certain things like the iPhone taptic system, which is more of a mechanical wave model, which is trying to, in the zero gravity environment of the exterior of the ISS, it would potentially get the dust off of the aluminum surface with very minimal effort and would be collected into a containment system. We did look into very, very low pressure vacuums, but they are very inefficient for this cause, especially in energy and cost. And the equations you see on the right hand side of your screen are some kinetic energy and amplitude wave equations that we are looking forward to researching more on and experimenting with to see what type of ways we need to get the dust off in efficient. So these are our two different types of potential wave makers. So one is the haptic system, which uses a motor that's offset in mass that rotates and creates a imbalance in increase in imbalance that will get the device to move back and forth. And the other one is a type of speaker system that doesn't use air but uses mechanical waves and will shoot through our device into the surface, which has and the edge of our model will have a silica thing to minimize potential damage.
So as we are saying, the first idea, some of the pros for it is it's simple. There's not a lot of moving parts, and it's more reliable. But some of the cons, it's a high risk, and we could damage the ISS, and the street sweeper might only be able to pick up the bigger particles, not the small ones.
So then we moved on to the electrostatic magnet, which has the pros of holding the particles very efficiently, and there's no risk of mechanical damage, but it's a very complex machine. The charge may not be strong enough for some of the particles, and the discharge could fry circuits on the exterior, so we decided not to go with that.
And finally, for the haptic device, it could be more compact, and there's also not as many moving parts, and it could be energy efficient. And some of the cons is that the vibrations could not be strong enough to lift the dust off the ISS, or it could be too strong to the point where it could dent the ISS. This was our first prototype of the shell. We went for a cylinder design, so it was more strong and stable. And as you can see, on the top on the right over here, that's where we collect the dust and put it in.
So here's an early CAD model of the shell that would have a screw fasten, and the container within the container would be a one-way flap that could be airtight, that would prevent the dust from getting contaminated by any chemicals or any even air on the ISS. So this outer edge would most likely have a thin layer of silica just to prevent the most likely aluminum shell from causing any sudden movements that could dent it or scratch it. And moving forward, our next test are prototyping an actual version of this that creates a vibration that is strong enough to move the talcum powder. And we have to design a system to funnel all the dust incredibly efficiently from the chamber into the airtight collection system. And we also have to develop a system for detection of a full dust container without any pressure or gravity. And thank you. Do you have any questions or comments?
Okay, so I think what I'm understanding is that your haptic system from Apple is going to vibrate the surface and then it comes off, but how does it get into your container?
It's within the shell, so anything within the shell would bounce up into the space, and then we have to figure out a way still to funnel it into the top compartment.
Okay, so how do your vibrations get to the the outside of the space station? Are you making contact with it?
There's a contact point at the outer ring of the shell.
So that's going to vibrate and then cause the dust particles to come in. Is that it?
Yes. If you think of glitter on a speaker, it's the same thing but without any sound or air.
Okay.
How big is this cup?
We modeled it to be about 4 to 5 inches by 6 inches tall. So it's handheld.
Yeah,
Okay.
but I guess where I'm going is the chamber inside, you've got this ring that makes contact with the station.
Yes.
And it's vibrating. The material that comes off, what's the distance it's going to have to traverse in order to get from the surface into your containment box?
About 4 to 5 inches.
That seems like a lot.
Yeah.
You can't you make that distance smaller? Why does it need to be 4 or 5 inches?
It didn't have to be. We just designed the model easily that way.
Okay.
So we could definitely make that shorter.
I think that would be the first step, right? Because we're not talking about a lot of particles, most likely, and that's a long way for them to be traversing.
Yeah.
So one of our difficulties is we're not necessarily going to be able to see these particles. And so the fact that you put it up against the wall and vibrate it, I don't know that I'm going to have particles there. So I'd like to try to cover more distance than just that that one surface area. Is there if I do this here and then go to another spot and another spot over and over, am I going to be able to do that, or am I going to lose particles that I might have captured in the first one?
There's definitely always the risk in this case of being able losing the particles, but with a one-way flap that we could funnel it into, and some sort of pressure to push them through it, I definitely think we could make this pretty efficient.
Where would you get that pressure from?
Yeah, that's my question. There is no pressure, right? You have no atmosphere.
We were thinking of putting a sweeper in it, a sweeper to the funnel.
Okay, so you're directing it in one towards one spot.
Yes.
But again, you're in a vacuum, right? So the notion of pressure is almost non-existent.
Yes, I think I misspoke on that. We were trying to use a sweeper, like a car wash sweeper.
Okay.
Okay. Well, I think you're dependent on. I'd really want to see some of this activity. So, how are you guys? Do you have one of these Taptic vibrational systems, or how are you going to work that?
We're going to design one very soon with an offset mass. That's still going to be the first design, and if that doesn't create a strong enough motion, we will look into a larger speaker one.
Okay. All right. So all of your vibration is going to be transferred through the contact with the space station through that ring. Is that right?
Yes.
Okay. All right. Now I because I haven't seen this, I think the only thing I can say is I want to see your demonstration of it working. Okay. So I look forward to seeing what you guys have for it. Okay.
So could you just have the astronaut vibrate it? Why do you need a mechanism to vibrate it? Could the astronaut just shake it?
If we have a stationary one and that just oscillates a little bit rather than a shaking motion, you'll have more that's a stable contact point, so not as much can leak out through the bottom.
Okay. But I see that with all the stuff in there, you will probably have, several inches to send that up to your container, which, by the way, I like, has no sharp edges and rounded corners, which is really cool.
I think I like your container, and that's actually the hardest part about this is how do I get particles inside without contaminating them with astronaut, food particles and skin particles. That's actually the harder part. The collection of them, I think, I kind of feel like you're looking for something like a really complicated way to collect them. I mean, is there a reason why you don't just use a cloth or a piece of
An
tape?
adhesive of some sort?
We don't want to contaminate it with an adhesive.
That's a good answer.
Yeah.
But
Yeah. Let me throw something out on that though. I understand that notion of contamination, but if you're analyzing this, you have a process of elimination.
Sure.
I mean, when you think about it, if you ran this through a mass spectrometer or something of that nature, you know what the signature of the adhesive is. You just eliminate that and then see what else you have.
Well,
Except the adhesive could change the nature of the cut. It's like exposing it to other things,
react with it. We don't know.
Yeah.
And the thing with the cloth is it seems that a lot of these particles are thought to be like quartz or mica or something like that, very like mineral-esque, which could, if we use a cloth to wipe it off, could scratch the aluminum on the ISS.
I'm not worried about scratching the aluminum too much. It is anodized, so it has essentially like a sapphire coating, and that's on the order of on the Mohs scale about a 9, which is pretty darn hard. So I mean, trying to wipe at it, I don't think is an issue. Okay. The crew move around on the outside and bump the outside of it. I don't think that they're going to be scratching it up very much. Okay. But so if you guys think that you can get some dust particles to kind of come off of the surface and float into your cup, I think you should give it a shot. And so using either talcum powder or diatomaceous earth will probably give you some pretty good results for that. Does that make sense?
Yeah.
Do you know what diatomaceous earth is?
It's of the same consistency. It has more minerals and stuff close to rock in it, right?
That's right. It's mostly silicon dioxide. Okay. Yeah. So they are very tiny particles. If one particle were sitting on your desk, you probably would not know it. So they're pretty tiny, and that's going to be similar to the size that we're talking about. Okay.
Mm-hmm. So, Glenn, do they not want to breathe in that diatomaceous earth?
Yeah, correct. So, I mean, don't snort it. That would be bad for you.
I think you'd have to make a pretty thick cloud of this stuff
to be dangerous.
I mean, the fact of the matter is, we are all inhaling particles of stuff every day. Oh. That's why allergies are such an issue for so many people on the planet.
That's true. Okay.
One question. All right. What do you think about using some sort of laser to view the dust on the outside?
I don't know. I'm not sure why that would show anything. What are you thinking there?
It's more like I was just thinking about how you can't really see a laser unless it reflects off of something, which could potentially be a particle in this scenario.
Could be. I mean, so you're going to see a lot of reflection just off the aluminum, right? But I don't know, like in a darkened room and you've got a beam of light, you can see sparkles kind of thing. Yeah. You probably would not see very much because in space, on the outside of the space station, we're not going to have a cloud, I would expect. it would be very little particles on the outside next to the space station. That's my expectation, but I could be wrong on that.
All right, fellas, thank you very much. I got to get you off to your next period.
Thank you so much. Have a great weekend.
Job,
and keep asking questions. Those are important.
of course.
Okay. So that's the end of your teams at Half Hollow, is that right?
Yes, you'll see one more of the teams on the 20th for biomed, but for DMP, I think that's it for today. And I know you've got a pretty long list of other folks to talk to. So thank you all for your time and your energy with all of this, and we'll catch up soon.
Yeah, thank you so much. They did a great job. And you enjoyed the weekend too.
Thank you. You as well. You well,
okay, bye-bye.
See you soon.
Yep. All right. So so now we're going to Glenelg in Maryland. And we are exactly 15 minutes late. So hopefully you're all right there, Glenelg.
Yeah. Yep.
Okay, good. It's good
We
to
have as
see
much
you.
time as you need, but you tell us what you need, okay?
Yeah, and remember, Dr. Gold, this is Ms. Grosser here. We only have the 2 Glenelg, even though there was 3 in the slot. So you'll catch back up after these next 2 groups here.
Awesome. That's what I like to hear.
Yeah.
Hey, Ray, great to hear from you.
Good hearing. Good seeing you guys.
Okay, team, whenever you're ready.
Well, we gotta share it. Google Chrome. Just guess and hope. Oh my gosh. Yeah, it's like
Here and through the screen. This is what happened each time yelling at you.
I have to allow it.
Oh, it's another one of those Mac things, I think. Yep. Same thing. These Mac kids.
So do I have to quit and reopen?
Yeah, quit reopen or something like that, I think is what it
All right, we'll be
does.
right back.
Okay. Yeah, we just have Glenelg, then Tri-County, then one more Glenelg. It's 3 more teams. Thank you, Glenn and Dave, for sticking with this. That's awesome. I really appreciate it. Your inputs are perfect.
Back on.
They're gonna jump back on.
Yeah, I think they're coming back in now. Now we can.
There.
Hey guys.
Why is there some room? Why is it? I just closed them all. Guess and check. That is not.
Looks like you're opening the PowerPoint here.
This one. That's the same one.
All right. We'll get on schedule here because I'll just tell them they're done for the day.
Bro.
That's okay.
Oh my gosh. You probably closed it by accident. It's just so dumb. Yeah, go back to the slideshow. No, it's right here.
Good. All right, I think we're getting there.
There we go. All right, there we go.
Awesome.
Hey,
Yep, I see something. Yes.
All right. All right, so we are the Lunar Ejecting Robot Group for Glenelg High School, and I'm Bennett Walsh.
I'm Mason Leitzel. And I'm Zachary Walsman.
Okay. And then, so our problem statement is that.
Well, guys, for the sake of time, we can skip the preliminary stuff. We know what the problem statement is. We really want to focus on your design ideas and any prototypes that you've built, okay?
Okay. Skip. All right, so this is like a past attempt that's
influencing one of our ideas. It's the Eagle Cam from Embry-Riddle Aeronautical University. It was built by students and faculty, and it was basically a box that had cameras facing each direction. It was a failed design, but due to like the durability of it, so we have to focus on the increasing the durability of ours. But the ideas of having a camera facing each way to be able to capture all the images we want is the thing we're really focusing on with this design.
So we came up with 15 different ideas for our robot and our ejection system. We came up with 11 that were for the robot and then 4 for the ejection system. And we had a few so the first 3 were all stationary shapes. It was just a box, pill, and triangle. The next 2 were expandable box and balls that would just expand out and the sides would rotate. And then it could move around with the camera on the inside to record. And then we had a weighted ball, which the goal of that was to control which way it landed, so where the camera was facing. And then we also had a 360 view with a panoramic ball that would be able to record in all directions. We also had a ball with spikes, and the goal of that was to stick it in the ground so that it wouldn't like roll away if it was on a hill or something like that, so that it would stay stationary. And then we had 3 vehicles. One was a car, one was a tank, and then one was a rover. We ended up going with the tank because we realized it would work the best because the car wouldn't really work in the sand as well, similar with the rover. So we went with the tank with tracks, and then we each have 2 motors on each side in order to control the steering. So then for the ejection system, we had 4 ideas. One of these was using a spring system to push the robot out. The other one was using ejector sleeves and pins. Another was using magnets and using whether they were repelling or attracting to just flip the magnet and repel it out. And then the last one was using a motor and a gear to just use a slider that just simply pushes it out. So that, although that one's very consistent out of the most, we went with a spring-loaded tube, which we later changed into a box this way so that it could be very consistent and simple. And all we need is a spring and then a pin to hold it back to essentially push the robot out of the ejection system. So this is our concept sketch for our tank. You can see we have a tank with 2 treads on the sides, and then we have a motor on each side to control the steering. And this is our first design where we had the camera mounted on top, but we realized in case it flipped over and landed upside down, then it wouldn't be able to record. So we changed it to a camera on the front and a camera on the back. And then we also added flashlights in case it's dark because the sun's being blocked by the other side of the moon. Then we have a battery, and then we're using a Raspberry Pi Zero because this is just a really small Raspberry Pi that'll work for our application with the motors and cameras and all.
So for this is one of our ideas for the spring to launch the robot out. This is the one we were talking about as a tube. We later changed this into like a box with a spring inside of it. The idea is that the spring's like always like compressed the whole way up. Then when it's time to have the robot exit the ejection system, you just pull one pin and it'll just pop out, and it'll hopefully stay within like 6 feet, so it won't be like the spring won't be too strong. It'll be 3 feet, and so like we just wanted to keep it closed the whole time. It's like probably the simplest one we looked at, so that's why we wanted to keep this one.
I like it.
This is the CAD version of it. This is more of a like how like it'll be in the box. Like the spring right now is like not compressed all the way, but it's all the way to the pin. So once you pull that pin, the robot will be against the spring. The robot will just come out, and it'll be.
Have you guys already bought a spring or?
No, we have to do that this week. We're gonna start building this week. We haven't built the ejection system yet, but some of the robot.
You know, one of the things you can do is just to adjust how much it compresses is just determined by how long the spring is. You might be able to cut some of it off, or just change the position of your pin, right?
Yeah.
Okay.
Yeah. All right. So this is our tank design. It's this size. This is just for cardboard. We want all all the motors and all the cameras and all the flashlight and all the stuff that makes it work to be in like this module, and the tank treads will obviously move it with the gears and stuff. This is like about the size we want, and we are cautious about the 15-ounce thing. So we're trying to find materials that are less than 15 ounces that could
can all fit in this and all stay within the box and get launched fine and be also like durable enough to withstand the fall and traveling around the moon.
We basically use the cardboard to build the dimensions so we have the dimensions for the box right here, and it fits like perfectly. So we build it out of cardboard so that we can follow the dimensions to make it like fill as much as we can and be able to hold all the stuff we need.
Very good.
And then this is the box that it just holds the dimensions.
It doesn't have the
if
spring
it fits.
showing, but that's the dimensions that it needs to fit within.
And then so this is our actual robot like prototype. So if you look right here, you can kind of see that yellow. That's our motor right there, and it controls this tank tread. And then on the other side, we have another motor that controls the other tank tread. And the code is going to be used so that like if there's something in the way, one tank tread moves and then it can turn the other way and vice versa.
That looks really good, guys. Can you stop sharing so you can point to more of your prototype there?
Yeah. All right. So, like I said, this yellow right here, if you can kind of see, is the motor. It's kind of encased by this whole cage.
Sure.
Put it in place. And then there's another motor right here. And then there's 3D printed like little like spacers kind of that hold this shaft into the motor because it doesn't really fit. So we had to do that. And then
very smart, gentlemen.
Like gears with shaft collars that hold the threads. And then this is the Raspberry Pi Zero that holds the wires. And then we need to get a battery because right now we only have it like plugged in. So we have to get a battery that it can just mount to it and work. And then where's the camera? The camera is right here. So we have to attach the camera to the
It's an
front.
Orange Pi camera. It's pretty small. It works with the Raspberry Pi, and we're gonna put another camera on the back of it. So there's like two cameras that we.
Now, and I love what you're doing. I think having two cameras is really smart. You've got two motors, and you can pivot and rotate your. Is this all fitting within the box so far?
Right now this is like a very rough mock-up. It's like an inch too wide, but that's because the like adapter right here with the spacers don't really work. So once we get it to adapt so that we don't have to use this 3D printed spacer, it'll fit in the box and we'll be good.
I am very impressed. I think you guys have a great start on there.
Thank you.
How's your power when you put the two cameras on there? Is that going to make it difficult?
No, they're very low power, so it should be able to work like fine.
Where is your battery located?
Oh, we don't have it yet, but we were gonna put it. We have a lot of space on top. Within like if you see the like size comparison, we have a lot of space up top that we can put it. So we were gonna put this up here with the battery, and then have something to protect it up there.
Okay.
Now, what happens when if it flips upside down from the fall?
We'll have it like encaged kind of like this, so it'll be fine. And we're gonna increase the size of these so that it gives us more space up here to.
It should work. It should work upside down, same as because it's like the treads are taller.
The weight distribution will just be a little different, but it shouldn't affect anything.
Okay, I'm very excited. Dave, you got some thoughts?
Yeah, I'm just curious. Within the system you have there, is there enough space between the two motors to put a battery?
Currently there isn't, but we're looking at two other motors that are much smaller and have a similar power output. So these next motors would just go right across the robot on this side, whereas right now they're laying sideways and takes up a lot of space on the inside.
And I'm just wondering if you get that configured. One of the things that we haven't really talked about much with any of the teams is, and I know that this is a prototype, so it's not representative, but you got a lot of wire there, right?
Yeah.
And all of that wire has to be pretty secure because, when you start dropping this, a little solder joint or something like that could snap pretty easily. The less wire you have, the simpler those connections between the battery and your motor, et cetera, could make a difference. And if it's all contained inside, there's less risk there. So just food for thought, not trying to direct your design ideas. What are you thinking about in terms of a housing? Are you going to 3D print a shell to protect the motors and and the wiring and your board?
We're trying to avoid like 3D printed parts. We're looking at aluminum to try and
Okay, perfect. But you're gonna fashion a shell to contain.
Yeah. So
Perfect.
in case everything like these like two like right now it's steel. Yeah, like these are steel right now, and we're trying to make these aluminum and just kind of make this like a whole. These are just two things connected to each other. But we're trying to make it like aluminum in case all the motors and all the like
and make them
flashlights.
taller.
Yeah.
I'm
So
impressed,
it's a little bit
guys.
more protected.
I like what
I think
you've
it
done
looks
so
really
far.
awesome.
I definitely do.
Yeah.
Flo,
Do
you got some thoughts?
you have any questions? No, I like that little robot.
We have one question.
Sure.
Yeah, so we were looking into the code and we were starting on that. And one of the things we realized we could do was we could record videos. And we were wondering if you guys just want pictures or if we should also add videos to that too.
Either or both, however you guys want to do it.
Okay.
All that we're trying to do is we are pretending that your phone is the lunar lander. You are sending the message from your thing, your robot to the phone, and it goes back to Earth. Does that make sense?
Yes.
Yeah.
And it could be pictures, and as many or as few as you want.
Okay.
Yeah.
Excellent job, team.
Nice job, guys.
For us.
Keep it up.
Yeah.
That's it for us.
Yep. Take some good videos of it testing. That would be cool. Okay. Thank you so much. And have a wonderful weekend there.
You too.
You too.
Thank you.
Thank you. All right. So we're gonna, I think, go back to Tri-County for our team and then back to Glenelg. And that's it. So Tri-County, you're up. Hello.
Hi. Hello.
How are you doing?
Good. How are you?
Good. It's good to see you.
Good to see you too. Do you want to share a screen? Oh, yeah.
Yep. Share your screen and introduce yourselves.
Yep, that one. And then share. Can you see it?
Yep.
Okay, awesome. And then wrong one. I meant to press slideshow. It's okay. Okay. Our group name is RKN Landing. My name is Riley. I'm Kylie.
And I'm Nathan.
And our project is Lunar Landing Legs in the Release System. We're from Tri-County, and normally we would be working with Miss Magus, but she's working in Houston. So right now we're working with Miss Bat.
Awesome.
Our problem statement, as engineering consultants, we need to create landing legs for a lunar lander to land on a slanted surface and create a release system in which the lander can release the two payloads so that it does not fall over on the langle and the payload is not damaged by the release. I'm the note taker administrator and lead prototyper. Kylie is the editor, scheduler, and corresponder. Nathan's the project manager, purchaser, accountant, and lead CAD designer.
Awesome.
All right, so our customer needs a safe landing so that all astronauts are not injured and no materials are damaged. That you also need a simple release system so that the two payloads are not dependent on the astronauts. Our restraints are that all legs and release systems must fit within the overall construction of the lander, that being the tomatoes and bean cans. The legs must support a landing of a minimum 6 degrees landing slope. Legs and release system must survive from a minimum drop height of 200 millimeters. The lander must stay vertical after landing and can't drop the payload during the descent or the landing on the surface. The payload can only be released after landing.
Through our research, we researched for the release system, we looked into electromagnets for holding the payload, like attaching the payload to our lunar lander during transportation and during like the landing. We also looked into like claw mechanisms and like how helicopters kind of holds like payloads while they transfer it. And then we also looked into like
springs and cables and like bungee cords for like the release and like slowly like lowering of the payload. We looked a lot into shock absorption and for the legs and for the payload for like when we're like releasing it. For the shock absorption, we looked into springs and like dampers, which are used to like prevent like vertical like bouncing and like movement during like landing or like droppage. Because like if we're like landing the legs or like dropping the payload, we don't want it to like smash down, but we don't want it to like bounce up and down or like tip over. So we looked into dampers, and we looked into having a spring within our leg with like it's like in a sealed part with a spring, a compression spring with Vaseline because that would work as a damper to like prevent the like bouncage of the legs and um of the legs and the payload. We also looked into cables, and then we also looked into a honeycomb pattern with like flexible 3D printed material to put on the bottom of our legs as like feet, as like a circle with like honeycomb pattern in it that was made with flexible 3D material so that it could like adjust like if there was like a rough surface or like rocks or like it wasn't like flat and had like bumps. And then we researched landing legs, and through our research we found out that like wider bases and like sometimes if the legs are spread like a little bit wider, it kind of helps because it like just like distributes the weight more evenly and it's just easier so it doesn't like tip over and it won't like wobble as much. And then we researched springs within our legs, and then we also looked into like spikes for the bottom of the feet so that could like kind of grip into the surface of the like moon and stuff. And then we also looked into different numbers of legs. We tested with 3 legs and 4 legs. And then we also started researching the moon environment and like microgravity and how that would affect our landing. And then the regolith and the moon dust and how that would also affect it, like if it was like under the feet.
Our initial ideas and designs for our landing legs, it has a lot, very like simple design, a lot of triangles because of the strong structure. The feet have we're thinking of having an adjustable joint so that it can move when it lands, since it will be on a slanted surface and allow more stability. The spikes on the bottom of the feet could also help dig into the regolith once it's landed and just allow for a little bit more structure once the release system starts working. For our release system, we have the idea of using claws that kind of wrap around the payload, and then when they let go, there could be cables that lower it slowly onto the ground. We also had the idea of having a shield around the payload and the bottom of the lunar lander that will hold it, and then the cables could also lower it from that shield. Our initial prototypes and tests, we had some struggle with 3D printing because that has been our main way of how we've built everything. We made these dovetail, adjustable, reusable, sliding bases that have little slots that we're able to take our landing legs and slide them into for testing. And this also fits onto our lander that we have over here. It fits onto the lander, so we're able to test it multiple times without attaching it to the lander or damaging anything. And then we have some videos of one successful video and then one failed video.
That's pretty good. Keep going.
And then
oh, play it again.
Yeah. I was going to slow it. Oh, sorry.
It
was really fast, so I was trying to slow it down.
We can slow it down, and then,
okay.
Yep.
It looks like you're dropping it onto hard asphalt. Is that correct?
Yeah.
Yeah. So we dropped it onto the asphalt because we have the tray of concrete as it's stated on the prototype website. but these legs were just a little bit too wide for that tray. So now our upcoming designs will be narrower so that we are able to do it inside of what you've given us to test it on.
We just thought the asphalt would be like more representative of it, like
Yeah.
as close as we could get without having to like make a new tray that was bigger.
Okay. Now remember, the tray has like about an inch of hardened concrete, and then you have about an inch of still dry concrete loose material, right?
Yes.
And so part of why I'm suggesting that is that loose material can also be something that helps slow your vehicle down.
Okay.
Just a thought for you,
Yeah,
okay?
that makes sense.
Because use all of the resources that are available, and if part of the friction comes from the moon itself, that's okay. Does that make sense?
Yes.
And so what did you learn from the failed video? Did you
That we needed like stronger and like thicker legs with like these legs had like a lot of like open space in them and like very like little material, so like they were very flimsy and they just like didn't like they couldn't like stand the power of like the impact as well.
And they didn't have like as many points of contact. So there were some loose bits on that prototype that weren't on the that didn't happen on that we didn't build with the working prototype.
Awesome. Yeah, you learned more from the failed video than the successful one.
Yeah. And so after we like did our testing and saw like what worked and what didn't, we adjusted our designs and we made some new designs to start prototyping with. And so one thing we're working on integrating is some more like shock absorption and like we're integrating like the springs with the damper into it. So like if you look at the picture like on the left, it has like we're gonna have a leg with like kind of like a tube, almost like a square tube with a spring in it. So and we're gonna probably seal off that kind of spring a little bit and then put the Vaseline in it to make it a damper so that it doesn't like bounce a lot, but it will still like also like absorb some of the landing force and like the impact from landing. And then we're also working on using the flexible 3D print material for the honeycomb pattern to put on the bottom of like the feet, what you call them, or what we would call them, the feet of the legs. And then we're also working on our release systems with the claws and the bungee cord because we need to do some more testing on that because we haven't really tested that as much. Yeah.
Excellent job, team. I really like it a lot. Keep going.
Our next steps, we will be using this point system, which we created to basically grade our legs and to figure out what works and what doesn't. We will also be using the same point system to grade our release systems. These are some of the questions we have after contacting some industry experts. So far, we have contacted MIT's Women in Aerospace Engineering, who we are currently conversing with. And we've also contacted Scott Rankin from Vulcan Springs.
And isn't he the founder of Vulcan Springs?
Yeah,
we had a phone call with him yesterday.
We didn't initially plan to call him specifically. We just called the company and then they sent us right to him.
Yeah, good, because he's helped before.
He was very helpful.
Yeah.
Very, very.
That's awesome.
That is impressive.
Okay. So I'm looking at your questions here. Protection. What kind of protection are you thinking about?
Like a physical barrier. So if there were to be a physical barrier, would we have to have this in like a can like the beans are for the release?
Okay. And I think the answer is no. The purpose of that particular shape and thing was so that if we have to send a bulldozer to the moon, I don't want to have to put it in a can, right? And so I wanted you to be able to think outside of a canister. How would you attach it? And so you are welcome to glue some kind of attachment points on there so that you can grab it or hold it the way you need to, or you've got the measurements, you can redraw it and add any kind of attachment points that you need to. Does that make sense?
Yes.
And so you just have to come up with how do you want to attach it. And it would be preferable, of course, if when it's set down, it's on its wheels so that the astronauts wouldn't have to like roll it over or something, right?
Yeah, that lines up with our next question. So we want it to land obviously flat with the wheels on the moon, but when during the landing, are we able to rotate the orientation of it?
You can have it attached to the lander in any fashion that you want, and then you can drop it the way you want.
Then,
but of course, let's try to put it on its wheels. Okay.
And
Very
then,
smart questions. Good job.
And then a big question for us is this last bit. We were wondering how much we can modify the rover because you said we can add stuff onto it. But we were wondering if this bit we could make adjustable so that we can fold it up or fold it like down so that's more compact during the landing.
Wow. That's a terrific question. And I'm going to ask Dave, what do you think, Dave? Do you think we should allow for, I mean, they want to hinge the backside of the rover kind of. Am I saying that right, team?
Yes. Yeah.
Okay. What do you think, Dave?
Initially, I don't have a problem with that.
And that's why I wanted. So by asking Dave, I was trying to give myself some more time.
Now, I mean, we're kind of in untrodden territory here, right? This hasn't been done before, so I would think initially giving some accommodations like that is probably a good idea. There's enough complexity to this that you guys can go ahead with this system. If it looks like it's going to become problematic, well, we can change it. But I'd like to see how you flesh this out.
You guys asked a great question, and I don't have a good reason to say no.
Yeah.
So I think if you guys want to make it fold, I think that is a wisdom that you guys deserve. So go ahead and give it a shot. Okay.
Okay.
And if somebody else asks me, I'll answer the same way. So.
Yeah.
All right.
I agree.
And then our one last question is that so we're wondering if we should like do the math to figure out like the gravity and weight of the lunar lander when we're prototyping and how we should do it for that, or if we should just prototype as we're doing now where we're not considering the weight of like the gravity that will be on the moon and the weight of everything.
If you want to share your calculations on what it looks like for the moon, I think that's wise, and it shows you've been thinking well on it. But of course, we're going to be testing it here on Earth. So do your demonstration for Earth gravity, and then we'll showing calculations for moon gravity and things like that is a smart idea. Okay.
Yeah, I totally agree. You're testing it here. We can't do anything to kind of augment that. But my thought as a former teacher is when it comes down to making a final decision, we might have 3 or 4 projects that we're looking at that all look very similar. They've met the design requirements, etc. So how do you pick one over the other? You know, having done a little bit more, taking some initiative on your part to actually submit those calculations, that could be, you know, a 1%er that works in your favor.
You bet.
So that's, I would say, go ahead and do it.
Okay.
Yeah, we love when you do math, applying your math.
All right. Did you have any comments, Flo?
No, it's really a great job, and I love that you're reaching out to different people to get their input, which is really helpful.
Hey, team, I had one more thought for you.
Mhm.
Could you go back to a picture where you showed the each of your landers, your lunar lander legs?
Yeah. Right here?
This one.
Yeah, that works. Okay. And one of the thoughts that I had is, one, I think that the way that you've got your can kind of, you've got plastic all the way around your can. I think that that's really smart. That makes for a lot of easy changes. The other thing I was going to suggest is that, consider when you had the 3 legs and it broke, the if you had a cable that wrapped around, so it went from one leg to the next leg to the next leg, it would add some extra force for your 4 legs, so that you're kind of tying them together, and they would add strength to each other. Does that make sense?
Yeah, that makes sense.
Just a thought for you. And that might help out with that breakout that you had. Okay? Excellent job, team. I'm very impressed. Another thought for you. When I came up with the lasagna pan, that was just the largest lasagna pan I had at my grocery store. If you guys found a larger lasagna pan that fits your lunar legs, that would be just fine for me. Does that make sense?
Yes.
Okay. All right. Good thinking, team. I'm very impressed. I think you're doing some great work here.
Yeah, this is a hard project and you're really attacking it well. So thank you so much. And you can always ask questions. Send me questions, because then if I try to answer, and then I'll send them on to Glenn. So that's
Wait. Let me ask one more question here.
Okay.
On that last slide that we were looking at, there was, can you explain the top middle picture? It looks like a disc with a couple of things that are poking out of the one surface.
So
that was
this piece?
Foot. No, the foot.
Yeah, the one in the middle.
Oh, this one?
Top middle.
The foot. The foot.
Oh, that's the foot.
Oh, this one? Yes,
Yeah.
that's the foot. So I was sorry, I didn't know
okay,
the
it's okay.
picture.
Stop sharing.
No, that's perfectly fine. I was just trying to understand what it was.
Yeah. So
excellent job, team.
Yeah, we have
Yeah.
leg right here if we want to show
Here,
it.
stop sharing. Let me see.
Stop sharing. Okay, yeah. So we have okay, so we have our landing legs right here. So this was the one that in the video that worked with the 4. And so this was one of our designs that this is the foot of it, where we had this like very small on this one because we wanted to start small, because we thought that if it was really big, they would have broken easier. And so, but that was just the foot of this one. And so we have 4 of these that are on our lander right now, but this was our first one that we did.
Excellent. I like it. It looks rather big for the cans that we have. However, I do not expect this lunar lander to be completely scaled, just because if you use motors or whatever, they're going to be way bigger than what the scale would call for. So show us your ideas and how they work, and we will analyze it for that. Okay? Excellent job, team.
Nice job.
Yeah, thank you so much.
Thank you so much. Is your teacher there?
Yeah, she's right here.
Hi, Miss Pat.
Hi.
You seem your teams are doing really well. Good job.
Yeah, keep it up. Everyone have a great weekend there.
Thank you. You too.
Okay, bye-bye. Great job. All right. And now we're going back to Glenelle. And this is the last one.
Hello. For the day or just for the time period?
For the day.
Oh my gosh. Okay.
Yeah,
I have it scheduled for the whole day, so I'm good.
Yeah, no. The other ones were Frontier, and we're not doing them.
Okay. All right. Hello, team. How are you doing?
We're doing good. How are y'all doing today?
Excellent. Good. What are you guys showing us today?
So we're the
Oh, I can't wait.
Okay, so hello everyone. I'm Rowan Zara. I'm Shrein Pasham.
I'm Neil Nayak.
and we're seniors from Glenelg High School. We're also chat, the CubeSat Heat Annihilation team. So we already know that you know the problem statement and all of that, and also
Yep.
this is our
Go ahead and
research.
pass there.
Yeah.
We're just gonna briefly go through this and then get to the design stuff.
Yeah.
So here are some of our survey results and some of the patents.
Yeah, and then we already know the design specifications. Of course, remove heat from the internal components and then off to the aluminum skin without convective cooling since there's no airflow in space. And then the 2U CubeSat along with the processor and the chip and the battery. And then some design viability. We already know about like the old heating failures and recent heating failures of CubeSats. And then we just made a matrix to compare different designs and
Hey, go back 2 slides.
Yeah, and of course, stop us if you want to ask any questions, of course. Yeah.
Okay, wait a minute. High failure rate, 8 out of the first 36. Wow.
Yeah. So
I
actually,
did not know that.
8 of the first 36 CubeSats were launched operational, which is obviously a really small proportion just to be launching an operational, not even successful, right? And then of the first 30 CubeSat failures, 24 were non-contact. Now, not all of those were overheating, but we do have multiple examples of overheating failures from the first 30. So,
interesting.
That is terrific knowledge. I had no idea we were attacking something so universal. Excellent job, team.
And so now we're going to get to the design development. So here's some of our concept sketches. On the left, we have a water cooling system, and this loop would be attached to 2 radiators that are mounted to the CubeSat and expel heat that way. And on the right, we have a deploying radiator that would be attached to the CubeSat and deployed directly from the body. And both of these CubeSats would be coated in an AZ93 space grade coating, which is used to regulate the amount of heat that hits the CubeSat. And here's our decision matrix. On the left, you can see our specifications, and we weighed each specification based on how much we thought it would impact our design outcome. After some careful consideration, we landed on the rigid insulator and radiator for our final solution.
Adding on to that from the decision matrix, this is our project proposal. We will be using radiators with AZ93 white paint coating with the emissivity of 0.9, allowing for the dissipation of the heat from the internal components, and they will be connected via aluminum conduction. The rest of the CubeSat will be covered with multi-layered insulating thermal blankets consisting of alternating layers of mylar and mesh, with the outside layer being capped on. And consulting with my dad, who's a thermal engineer at Vertex Aerospace, we found that AZ93 paint is too expensive for high schoolers like us to obtain, so we will be swapping this with silver Teflon with an emissivity of 0.8. Additionally, these materials are commonly used on the ISS and other satellites in space today, so we know that these materials are known to work. And before we created our CAD design, we did some hand calculations to find the size of the radiator needed to be able to disperse the 120 degrees Celsius. So here we're using a bunch of the constants from the materials that we used, including the absorptivity and emissivity from the silver Teflon. And on the left here, we can see the calculations of the conduction and the effect of the aluminum conduction on the temperature with using the conductivity of aluminum, which is 237 watts per meter Kelvin, and creating a very small change in temperature being almost negligible for the project.
And then here's our CAD design of our rigid insulator and radiator. And then here's an animation of it, of the exploded view.
Okay.
And then going more into the actual like parts, you can see at the bottom we have the chip and the battery, which is the innermost layers, connected to the actual aluminum conduction block, which is what we were talking about earlier for the heat loss, connected to the aluminum plate, which has the MLI blankets and silver Teflon laying right on top of it.
And before creating our prototype, keep
going.
So before creating our prototype, we needed to make a thermal analysis, and we were using the hot case. And here is a animation of our CubeSat orbiting around the Earth from the sun's perspective. As you can see, the CubeSat is perpendicular to the sun with a rotation of 45 degrees to ensure that it has the greatest cross-sectional area exposed to the sun, meaning that the CubeSat can reach the highest possible temperatures. And here's a more in-depth analysis of the CubeSat without the insulators. Here you can see that because of the aluminum shell's conductivity, the temperature is spread throughout the entirety of the CubeSat, with the radiators being slightly higher in temperature because they are not covered by insulating blankets. On the inside of the CubeSat, you can see that the internal components are also slightly higher temperature than the rest of the CubeSat because they are producing heat themselves. And despite this, Despite this, they are below 120 degrees Celsius, operating within the temperatures, meaning that our heat transfer method works. And so on the back of the CubeSat, you can see that it is slightly lower temperatures because it is facing away from the sun.
However, all of it is within 117 degrees Celsius, as you can see on the left, which shows that the aluminum is actually evenly dispersing the heat throughout the CubeSat. And then looking at the MLI blankets on top of the CubeSat, you can see once again the radiators are still 117 degrees Celsius. However, around we have the yellow and orange gradients. That's the MLI blankets next to the radiators. And you can see on the scale, it has completely shifted all the way down to negative 135 degrees Celsius. You can see it's significantly lower because the MLI blankets are kind of that preventative measure so that the heat doesn't get to the components from the sun. And you can see how they're changing for each side. And then if we look here as well, this is the back side, you can see they're significantly colder. Also, the heat from the earth is also playing a role into this. So that's why each side is a little bit different. But then it's still significantly lower. It shows how our MLI blankets are actually in effect. And then once again, you can see the actual internal components, the chip and the battery, are still 117 degrees Celsius. So that shows how like the conduction is negligible from the radiator to the actual components.
And for our prototype development, we started with creating the mock-up. This is specifically designed to mimic the appearance of the CubeSat that we will make. And taking a look at our testing setup, here we can see
we do actually have this setup. We're just going to briefly go over the picture real quick and then show you guys the actual dome.
Yeah. Sure. So here we can see two Takeo circuit heaters, and these are strips that generate heat, and they're meant to simulate the battery and the processing chip in our design. We hooked them up to variable power supplies and measured the voltage so that they generate 5 watts of heat each. And attached to these strips are these sensors, which go over to this software over here. And this is a time lapse of our testing, and the software records the heat buildup in each of the strips over time. And we test it for 7 minutes. Here's some of the results from the testing. The dashed line is to represent the actual data, and the solid line is the line of best fit. What we really took away from this is that the slope of both lines is near identical, meaning that the change in temperature per second is almost identical for both strips, meaning that we can proceed with testing as planned. And so for future work, we have only done the hot case analysis for now, but we will need to do the cold case analysis where the CubeSat is facing directly away from the sun, so the internal components may freeze, falling under operating temperature. Additionally, we need to finalize our prototype. Right now, we have several of the materials that we need to create it, including the MLI blankets and silver Teflon, through borrowing them from Goddard Space Center. And we need to finalizing the design testing. We are contacting several institutions for access to vacuum chambers so we can further our testing in an environment without convection.
And here are our sources. And of course, do you guys have any questions for us?
Let's show them.
Actually, first, do you want to see our actual
model? We do.
Yes,
please.
Turn up.
And did your dad work at Goddard then? They are right near Goddard Space Flight Center.
They work. He works with them. Like
that's what they.
Yeah.
I'm gonna bring this over here. So tell me if you can see everything because I can't see the webcam. You guys.
Okay, tilt it down a little bit.
Tilt it down.
Yeah.
So right here, these are our two variable power supplies, and these are our heaters. And right here, this is our silver Teflon that we'll be using on our.
You can see that.
Here, this is a slightly smaller aluminum tube than the one described in the PDF.
However, you forget from the design parameters, but we are going to order the once we make sure this all is good, we're going to order our proper size aluminum tubing.
Yeah, for our actual design.
Sounds good.
I'm going to turn these on real quick.
Yeah, and then here you can see that we have our MLI blankets. These consist of 12 layers, and so and the capped on layer on the top.
Yeah, you can actually see the. I'm not sure if you can see right now.
That's the real stuff, huh?
Can you see it? Like how it's like multi-layered.
Yes, I can see that.
Yeah. What's
the purpose of all those layers? What do you think?
So they allow for the radiation, like the.
It's basically what the MLI blankets are doing is they're basically stopping the solar radiation from the sun, and all the layers, the alternating layers of the mylar and the mesh, basically is a way of it making so it doesn't reach the metal. That's essentially what the goal of the 12 layers of each is.
Yeah, and part of what is also related to the vacuum that's in between each of them. Does that make sense?
Yeah.
So
Additionally,
excellent explanation. Good job.
So when we're cutting it up, we will be using this insulation tape to ensure that there's no heat that can get in.
Heat loss,
Okay.
Yeah, heat loss.
All right, so right now these are heated up, 22 volts. They are currently different resistors, so the voltage is going to be slightly different, but they do end up being 5 watts each. I promise you they're heating up. I'm holding.
You can see
Yeah, okay, actually.
So right now, this is live data. It is increasing as the heaters are heating up.
Mm-hmm.
Yeah, can you see it?
Nice.
Yeah, and then it's mainly the battery and processor. This is going to be the cool side, so you can see those are like 22, 25 degrees. They're not going to change right now, but that's just to show how it was originally, and this is how it's increasing.
Point your camera down a little bit more here.
Yeah. Furthermore, once we have a vacuum chamber, there will be less effect of convection, because right now, because there's air on these heaters and the sensors, the air is cooling them down, skewing the cells.
Yeah, we know that in the vacuum, like in a vacuum chamber, it's going to be significantly hotter without the airflow. So
that's right. Yeah. Well, and right now you also have the table that's getting warmed up by that, right?
Well. Yeah, that as well.
Okay, you guys are doing a great job here. Now, why are you choosing to use those heaters as opposed to getting the fish warmers?
So because we have a budget of $100, we wanted to save as much money as possible
yeah, we're currently borrowing these from Goddard. You can buy them for around $10. It's like a generic circuit heater, right? You can buy it for like $10 on eBay as well. But like we were provided these from Goddard, so that's why we chose to just go with these instead of the fish tank ones that most groups are using.
And using the power supplies, we were able to change the voltage of each of the heaters. So
yeah, we have them wired in parallel circuits right now, just so that we can.
So just be aware. So those heaters, yes, they're the same 5 watts, but of course they're also much smoother. Hold on just a second. So here you can see the heaters that I've got. Notice how they've got a surface that's bumpy, and so it makes it difficult for me to make good contact with the metal. And so that's also something I wanted you to be seeing as well. Does that make sense?
Yeah. So additionally, we did research on using materialized paste, so to make sure that the conduction is completely connected.
Okay.
Just to get that.
The other question, I also noticed that you were using like a block of aluminum, as opposed. I didn't see you using any heat pipes. Is there a reason why you chose to not use heat pipes?
We could use like a compressed heat pipe, like kind of like in a laptop, but like we just chose to go with aluminum blocks for like that cross-sectional area, and then the length of it. It just made it easier for our conduction equations, and we thought it made more sense for our application.
And that's fine. It's not a criticism. It's just a question.
Yeah.
Excellent job, team. Keep going.
Mm-hmm.
Yeah. Any other questions or feedback?
So, Glenn, do they need to get those fish tank heaters, or can they use what they're doing?
Well, what they're using from Goddard is a smart idea, but it doesn't represent exactly what we're trying to work on. So see if you can work into getting these, and it's more about the size as well as that surface, the bumpiness of it that affects how some of this is going to work. Yeah. So yeah, I'd prefer you be working with these kind of heaters if possible. Okay.
We will. With that new information, we definitely will.
Okay. Additionally, we had a question. So we did some research, and we know that CubeSats are usually ejected once they're in space. So we were wondering if there was like what the tolerance was from the CubeSat to the ejector.
Yeah, so basically, like within the deployer, we want to make sure there's no interferences or anything with any of our materials, like the MLI blankets on that side. So we want to make sure that we have enough tolerance for those materials on the outside.
Excellent question. If you go into the solar panel deployer project, you can see there's a cross section and also photos of the CubeSat deployers, and that should give you all the information you're looking for. Is that okay?
Yeah, thank you.
So taking the CubeSat, the solar panel deployers into account, okay, wait, yeah, okay, you just answered my question. Yeah. Thank you.
Yeah, no, but that's an important question that you're asking, because the deployer has rails to send out the CubeSats, and it uses a spring, and it's got to be really uniform, I would think, and you can't have material that's going to stop that system.
For
So-
us right now, it is uniform and it's pretty thin as well, so we don't think it's gonna have much interference, but we wanted to double check before we went full scale into this project.
Yeah, so
And that makes sense.
Yeah, so the blankets will protrude about 0.3 centimeters. So is that within the tolerance?
We'll check.
All right, yeah, we'll check on the.
Check
So
out
there'll
the
be-
drawings.
There will be areas where that could, so the location where the rails are in the corners, that would be a problem. However, on the other areas between the rails, it may not. And so there are certain areas where I think it will work just fine, and other areas where you may have a difficulty. Just for your knowledge, so it's in the solar panel deployer, but I will make an update so that it's in your presentation as well. Okay.
Thank you.
Yeah, we're gonna do some research on that. Thank you.
Good
Excellent
observation.
job, guys.
Yeah.
Nice
Dave, any
job,
thoughts?
guys. No, you guys
Yeah.
are doing a tremendous job.
Yeah, that's what I gave you 5 stars on that job. But you do need to look into that deployer issue and you can ask questions because I actually have students making the parts for that deployer. So I'll have a lot of information about it.
Do you think we could get like in contact with them to be able to like maybe even have these parts to put on our CubeSat as well?
No.
No, but you wouldn't be able to get the parts, but you should, with the dimensions that I've given you, you can print those out.
Yeah.
Is that okay?
Yes, of course. Yeah, that's fine.
Excellent. Okay.
I mean, that was our primary.
Good job, team.
Thank you.
Thank you, guys.
Yep. Thank you so much. We really appreciate all that work. And thank your dad also for supporting this project with you. That's really cool too. So you can always email me questions, and if I don't know the answer, I'll have Glenn or somebody even in manufacturing can help if you have those questions about the CubeSat deployers, which is really cool. So enjoy the weekend.
You too.
Yep, you too.
Is
Thank you.
Mr. Gershner there? Is your
Glenn,
teacher there?
Yeah.
Don't get off yet. I got a question for you.
Okay.
Okay.
Are we doing all right? Mr. Gershner, do you have any questions?
No, I think we're all good. We what, 10 days? We got all the groups covered in the Northeast, the Pac Northwest, basically. That's pretty good.
Actually, I have one more in Somerset, New Jersey I didn't do. They needed extra time, but otherwise
Ray.
we're good.
Ray, I like the beard. It's looking sharp. Keep it up, man.
Working on it.
And
We
Ray,
always are.
if you have any preference for what day you want to go to New Jersey.
I was going to ask you, I think one of the 2 days we have class, I think was the first day. So that was my first preference. But then it really came down to like, do you have 90% of the teams going one day over the other?
Yeah, I'm trying to. So it's Passaic County Technical Institute has a ton of teams. They have PCTI and then they have PCTI STEM. I'm trying to split them. So then then we could split the other teams whichever way. So
Yeah, I think the first day was a class day, so it's just one less class period these kids miss during that day, which I think was going to be. Oh, is that what are you looking at?
26.
26 and 27, I think were the dates. Yeah. So probably the February 26th would be our day that I'm shooting for.
Awesome. Okay. Perfect. Thank you so much. You enjoy the weekend there.
All right. You guys as well.
Okay. Bye-bye. I'm going to